one-dimensional motion. And we started the year by looking at one-dimensional motion that was constant rate motion. Then we said after that, what if the motion is accelerated? What if it speeds up? Or what if it slows down? That was the second part to it. Now we're going to say, now that we have accelerated motion and constant motion, can we look at motion that is launched at some sort of an angle? Okay? Or can we look at motion that's launched horizontally, but then starts to fall towards the ground? So we're going to incorporate this section, this topic, for a couple of days we're going to spend on this topic. We're going to incorporate gravity in the vertical direction, just like we have been, right? For the free fall problems we've done now, or the launch straight up problem where gravity pulls it down. Now we're also going to incorporate constant motion in the horizontal direction. Because when an object is fired horizontally, gravity is the only thing pulling it down. It still wants to move left to right the whole time. Now, air resistance does have a tendency to slow things down, but we're going to look at problems that don't involve air resistance. Then we're going to maybe later on say, what if air resistance is included, like on your test, right? When I said G is now 3/4 of G because we're taking into account air resistance. That's not the traditional way you would do it, because air resistance doesn't just affect G, it affects a couple other things actually. But that was a simplification of that idea. So we're going to do that a lot in this section. Now, to start, what I want to do is a quick demonstration. And I want to show you this apparatus first because we're going to use it a couple times this year. Now, we're also going to use simpler apparatuses, and we're also going to look at like computer simulation. But projectile motion is not the easiest thing to really study in the lab because, again, we need to launch projectiles. So we might go down to the gym for a day or two to look as well. So the way this apparatus works, and you can probably hopefully see from where you're sitting, I'm trying to hold it up a little bit here, is there are two buttons here first, arm and launch. You have to press both, kind of like you see those old movies where there's two keys to launch a nuclear missile or a nuclear warhead. I'm trying to make the same idea, but you need to press both. This puts pressure in the line. So you'll see there's a pressure gauge right here, barometer, pressure gauge on the side of here, and you can pump more air, compressed air, behind where the projectile is waiting. So there's one projectile here, and there's another projectile sitting right here on the side. This one is just sitting on a little hole inside it. It's just kind of sitting on this rest here. Okay? Now, we can angle this, and you'll see a protractor here. In a little bit, we're going to do that. Not today, but in a couple of days, we're going to see what happens if it's angled. Now, in addition, they also give us what's called an internal photo gate distance here. If you remember the photo gate we did with the picket fence, remember you dropped the picket fence and went through that little photo gate? There's a photo gate in here that is exactly 5 centimeters. Same distance between those bandwidths, if you recall, from the picket fence. The idea is that it can measure the position of a projectile 2 different times, and therefore calculate and approximate what we call muzzle velocity, or initial velocity. So the photo gate allows the computer device in here, when connected, which I'm not going to connect today because we don't care about it actually today. When I connect it to the vernier device, it'll give us the initial velocity with which it was launched. The angle can be measured here with the actual protractor. The amount of pressure simply affects the initial velocity coming out of the actual muzzle, or out of the rifle, we should call it. The rifle is just the actual chamber itself. Not a real rifle. What else? Now there's a nice level in the front. The reason for the level here is so that you know when you're launching something horizontally. Today's concept is going to be about launching things horizontally. So this needs to be perfect. And I already tested it out because it's wobbling right now because I'm moving my hand. But this little air bubble here will be centered in the middle that tells you that it's level or it's on level ground. And I can adjust this by tightening or loosening these two knobs here and then adjusting the angle at which it's launched. So we're going to do a lab together as a group in a couple days. You're also going to do a couple simulations on a computer with a program, and we're probably also going to go down to the gym. So we're going to do a lot of different different types of labs for this. But when we do this one, we only have one of these devices. I can't really get 5 of them to launch across the room because it gets crazy. So when I do this, I kind of just do a demonstration with this one. So for today, I'm going to quickly demo what we're going to be talking about for the beginning of the lesson. I'm trying to think anything else here. Is this page? No, it should be good. So on the back, they also give you a little diagram here, and it tells you the launch point. So usually, without this little barrel here, the launch projectile is actually contained inside of here. I can show you what I mean. This comes right out. That's going to roll. So let me grab it. So the projectile is normally in here, okay, and it gets launched out. But because we're using this one today, okay, we're going to launch one on the side as well. So the projectile is currently only right here. But normally, those back here. And that's the reason with this diagram. So you know what the initial height is, what you know what the initial displacement is, and it's all given in centimeters. So that when you look at y0 and x0, you have the correct coordinates for your initial positions. Okay? So I'm just going to move over here on the side for a minute. Okay? Now, what I want you to think about is this. If you know the answer, you don't have to be like spoiler about it, but maybe talk to the person next to you for a moment, which I'm going to have you do. You don't have to call out the answer if you've seen this already. But this projectile here on the inside is going to be launched horizontally. This projectile that's right here, as soon as this one is launched, this little metal bar is going to retract. And as this bar retracts, this object's going to be dropped. So I used to do this with some tennis balls earlier on in the year. And the tennis balls work, but they're not as precise. And what we would do with the tennis balls is one person would roll a tennis ball, and as soon as he got to the end of the table, the other person would drop the other tennis ball, as the first one was exiting the table. So when it was like right here at the very edge of the table coming off, and it's going to fall in this pattern, right, in that arced curve or parabolic curve, the other ball was dropped. And the question was, discuss what's happening in the problem. So before I do this, spend a minute, literally a minute, talk to the person next to you. What do you think is going to happen with these two projectiles? That's the question. Okay, spend literally a minute talking. Good. Arguments. What do you think? As a result of your conversation, what do you or your partner think, or did you differ in opinion? What do you think is going to happen? Who wants to give some sort of statement? Nick?
Do you think the balls are going to hit the floor at the same time?
Okay. Nick thinks the balls are going to hit the floor at the same time. Do people disagree, agree, simply show of hands if you agree with Nick? If you agree with Nick. Okay? If you disagree with Nick, what's your opinion? If you disagree with Nick, what's your opinion? Remember, there's no wrong answer right now. Okay? There really isn't a wrong answer. You're taking a hypothesis. That's what science is about. So if you thought something different, please give that information. Okay?
I don't know, I thought they might hit it at different times just because one has just a straight line to travel and the other one has to travel in a curve.
The second one has to travel further, the first one falls straight down. Okay? What else? Yeah?
Yeah, I thought that maybe they hit at different times because one has velocity going this way while the other one is just going straight down.
So one's a free fall and one has velocity to it. Yeah, good ideas. And the idea behind this is that there isn't a right answer until you see it happen, right? And then we'll talk about why what happened, because that's what's more important afterward. So some of you might know, oh, if I think about the math behind this, I can figure it out. And there is a lot of math and physics behind what's happening here, and you can determine that answer. But we're going to show it first as a demonstration. So give me 1 second. Make sure this is nice and pumped. I want you to assist those hands here. You notice the thing moving? Okay, so here's what I want you to do. You can kind of stand and go to look, but you really need to listen, okay? Because they're both plastic marbles, so you'll hear them hit. So the goal is to listen, okay? That's good. I want to make sure everything's right. Okay? 3, 2, 1. Hold on. I think this needs to be plugged in. Now, it should have to be plugged in. Hold on. It should have to be.
No one's expecting it, so someone gets like a concussion.
I think it's not launched.
I think so. It like bounces off and breaks the window.
Ah, there we go. Okay. I think that was all that.
That's my hypothesis. It will break a window.
Alright, try it one more time. 3, 2, 1. Let's try it one more time. So, by the way, I want to point something out. Nick, can you come to the front and help me with something? Nick, where do you think that, I saw you standing, that's why, do you see where that ball is approximately? Give me a spot, yeah, okay, so stay around that area, it's not going to be there. I might, it's not. So that's where it landed, the first one, right? The second one that dropped landed directly below it. So I want to see if this can land it. But again, listen, okay? 3, 2. What are we hearing? What are we hearing? It's tough, right? I'm gonna go a little bit slower. Yeah, if you get a video, it'd be great. Put the wrong one in. Hold on, hold on. It's not. That was not the work. I put the wrong one in. There's a little like hole on the side, or else it won't work. Yeah, Nick, if you can get a video from the ground. So I'm purposely not going to pump it up too much this time. Okay, I launched the first one a little further. The second one maybe like halfway across the room. Ready? Yeah. 3, 2, 1. Let's do it again. Again, why am I doing this over and over? Because if it were me and I were a student and I didn't know the answer, I would run trials, right? To really see what's happening over and over. If I'm not sure, I would keep running those trials and maybe vary stuff along the way that I needed. So what is my variable right now? What do I keep varying?
The pressure.
The pressure in the line, which then varies the
Initial velocity.
Okay, so I'm seeing what the initial velocity has an effect. All right, Nick, here we go. 3, 2, 1. Any conclusions by now? Is there a couple enough trials here? Nick, did you get a good view of that?
Yeah.
Can you airplay from your phone?
Yes.
Can you find physics lab on your phone? I might have to disconnect mine. Hang on. Let's take a look at it in slow-mo for a second.
I do too. We need to sing a lot.
All right, take a look.
This soundtrack is ridiculously hard. Let my people go. Stop saying insanely hard. Val Kilmer plays both God
Help me
and
find the discoverable. Yeah, hold on.
anything comedic about that. I don't know exactly.
Okay, look for Mark's.
Sandra Bullock, Nigeria.
Virginia getting it. Sorry.
No, the animated movie that we got
Mark's not
it's
good.
Oh.
Just gotta be the way.
I like to get the
249. All right, let's take a look at the video real quick. Nick's going to show it to us. Can you turn your phone? Is it turn horizontal?
Oh, there. A nice view.
All right, here we go. Let's take a look. Follow the. We should have done it with a black background. I didn't realize it's not going to be tough. That's your way. Maybe zoom out a little bit. Yeah. So you want to see the floor? Nice. So we see one of them about to the floor. Where's the other one now? Oh, okay. Get it right with this again. Ready? Set, boom. Isn't that awesome?
That's really cool.
It's not something you'd expect either for the reasons you all stated. One has velocity, one doesn't initially. You have to hit the ground. Now, the crazy part is, I don't know if you picked up on it, depending upon where I launch it, there is a small discrepancy, and you said it the first time. The first one I launched, like almost at the podium, Caroline goes, it was close, but I think it was actually a little off. And she's right, it was a little bit off. Why was the first one slightly off, and the other ones were much better runs? Jack, what do you think?
Because the further it goes, the more air it's like running into.
Yeah. Air resistance affects things more the longer it's in the air, or the further it travels. So as a result, the first one that was launched all the way here was being slowed down by air resistance more than the other ones that were landing over here. The one that was a free fall was practically not being slowed down at all, but hitting obviously for this much distance, right? But this one is traveling through the air. The other effect, Morgan.
So if you increase the higher the initial velocity, the less equal it'll be, or
The higher, yes, correct. The more initial velocity, the further it's going to travel, the more it's in the air while moving horizontally. Motion is what creates air resistance. Do this real quick. Take your hand like this, okay, and just don't hit the person next to you. Just move it like this very slowly. Very slowly. Now do this, ready? Now, move it a little faster, and you show a little coil, right? Now do this. Turn your hand, and then go. So it's perpendicular body, then do it. So if you do this underwater, it's not as obvious right now because the fluid that we're submerged in is oxygen, well, a combination of that. But the fluid that we're submerged in does not create much of a viscous force because it's not very dense. If you've done this before in the pool or in the ocean, you can literally feel a lot of resistance when you do this. Not as much when you do this, and if you move really slow, you barely feel any resistance at all. The air resistance or fluid resistance is a function of your velocity and your area, the cross-sectional area in contact with that fluid. So if I move faster, higher air resistance because I'm moving faster. If I turn my hand like this, higher air resistance because, again, my hand has more area when it's turned this way. So in the examples that were launched further, it was traveling at a higher velocity. Higher velocity meant more air resistance, which is what makes the further launches not as good of a demonstration as the shorter launches themselves. Now, let's go into, we're going to see now, why this is all true. Next thing. Yeah. Let's go into why this is all true today, because that's really what's way more important. Like, we can see it, and that's great. And science is like, half of science is empirical, right? Where you look at stuff, you study things, you look at relationships, you recognize, like in chemistry last year, for like the gas constants and stuff, they're not just made up. They're determined from experimentation. The same concept applies here. There was definitely a time where people didn't have a device like this, and they did exactly what I was saying earlier, where they literally grabbed two tennis balls and tried the same thing. One ball was rolled off, one was dropped, and they hit the ground at approximately the same time. Now the problem with that is what?
When were tennis balls?
Two tennis balls, yeah.
When were tennis balls invented?
Oh, that is the problem too. Any object would work. I like that answer. When were tennis balls? What's the problem with that in general, though? That experiment was the problem, if I'm saying. What do you think? What's the problem? Christina?
It's good if you're throwing it yourself because you vary the amount of initial velocity you put on it.
Yeah, there's human error involved, pretty much, right? I'm going to roll this object to the table, that's fine, but the person waiting here has to time it. Like, ready, set, drop. Like, how do you know that this is being launched, meaning it's exiting the table, at the same moment you're dropping it? There's a lot of room for error there. So having this device here, if you notice what happens, when this projectile is launched, there's a little nubby here. It's not the size of the word, a pin. There's a pin here. Hold on. Okay. So take a look. I know it's tough to see, but look over here. For a close-up, you can probably see if you maybe stand up. There's a pin on the side. When I put this one projectile in here, the other pin comes out. So when this projectile gets launched, the pin retracts at the exact same moment. And this projectile has a little hole in it. So this projectile is literally sitting on the pin. So I take this projectile and rest it so that it's sitting on the pin. When this one falls out, the pin retracts. At the exact same moment, it drops the second one. So these two projectiles are launched at the same moment. To do that experimentally and like just walk in and trying with tennis balls probably wouldn't work too well. Okay? So let's talk about now why this is true, why what we're seeing happening is actually happening. So we're going to start by looking at projectile motion. We're going to start by looking at projectile motion here. And the idea behind projectile motion is this. Any object that's under the influence of gravity, while traveling horizontally, is considered a projectile. And that's probably actually on the next slide if we go ahead and take a look at that slide there to see. Yeah. So a projectile, again, is projectile itself is any moving object. You model as a point, a physical point in space. But projectile motion has to have some sort of vertical velocity with some sort of horizontal. And the vertical velocity doesn't have to be in the beginning. It could be, like we said, a free fall. So a free fall itself, I just dropped this, right? That's just one-dimensional kinematic motion. But when we launched the object instead, it was only launched horizontally. So we would say it only has velocity in the x direction to start. But what happens as it falls toward the ground? What happens as it falls toward the ground? What do we think? So it only has horizontal velocity to start. But as it falls toward the ground, what do we think is happening? What do we think is happening? Just let me look at it. Gravity, I like it. So, as a result of gravity, you're on the right track. It has acceleration. Gravity. What does gravity do? What does it cause the object to do?
Move in the negative y direction.
Move in the negative y direction. So, although this was only launched with velocity x. What does it pick up along the way? It picks up vy, vertical velocity. So these problems that we're going to start this chapter or this section with are going to be launched horizontally. That's what today's focus is going to be. Then, after a couple days, after we do a demo or so, we're going to take, or a lab or so, we're going to take a look at launched at an angle. And you'll see that at the end of the homework, we didn't specify which is which. Okay, you'll notice that a little asterisk. The ones with the asterisks are launched at an angle. You're going to do those later, like next week or over the weekend. This kind of stuff we're going to take a look at today. So when you're practicing the homework, you're going to do horizontally fired projectiles. Now, the person in the diagram is a track star running with horizontal velocity. Then this person jumps. When the person jumps, the person gains vertical velocity and had horizontal the whole time. And when this person gains vertical velocity, this person is then going to lose vertical velocity and come back down. Or it's going to slowly lose their velocity, get to the top, stop moving vertically, and then start to fall back down. The same concept as the max height problem. The max height problem is so important, and I kept saying that. When it gets to the top, what does it do? It stops. That's why we kept setting v equal to 0 for max height problems. The same concept applies when this person reaches max height, but it's only the vertical velocity that's 0 there. The horizontal velocity, well, that part, that's going to be the same the whole time. Why is this never going to change? Why is the horizontal velocity of the object or the projectile never going to change? Jack, what do you think?
Well, since we're assuming, or like not including air resistance, there's nothing to slow down.
There's no decelerating or accelerating entity, force, that's causing it to change horizontally. What's changing vertically again? What'd you say, Justin? What was it vertically? Yeah, it's just gravity, right? Pulling it down. But if you throw something like a baseball, gravity pulls it down. So a baseball, although seemingly horizontal when a pitcher pitches, or a softball pitcher pitching, is not actually horizontal, perfect. It drops. And we're going to see in this chapter the idea of like, if you take a bow and arrow and you launch it, the further away you are, the more that bow and arrow is going to drop toward the ground. So that's why, if you know, like in like those movies, what's the movie? What is it? No, it's with Bradley Cooper. He's a sniper. What is it called? American Sniper. Is that what it's called? American Sniper?
Yeah, I think it's called American.
Yeah.
Anyway, in these, it's not Bradley Cooper.
I think Bradley Cooper was in Lone Survivor.
Sorry, yeah. Anyway, so some actor, whatever. I used to reference Kiefer Sutherland from 24. Did anyone ever watch the series 24? It's pretty awesome, actually. It's really
The
awesome.
last survivor.
Anyway, so when a sniper were to shoot, or when somebody were to shoot a bow and arrow at a long distance, if I wanted to hit the cabinet, which was eye level with me, I can't just release. I have to angle it up a little bit, right? Because I have to take into account the fact that there's going to be what's called drop, or object drop, or bullet drop is a phrase. Okay? Anyway, the concept here is that it's moving vertically due to gravity, but horizontally, it's never going to lose or gain velocity. We're going to assume no air resistance for now. So, we have an image here of a soccer player heading a soccer ball, right? And there are two paths taken here. The path A is the idealized path. If path A is the idealized path, what would path B be? What would path B be? The realistic path, okay? So realistically, what we notice for these, we notice that the projectile itself will be parabolic and will have perfect symmetry with projectiles. But if it's launched with some air resistance, it's going to slow down along the way. So trajectory B is literally just slowing down. Oh, we should just happy birthday to her. Do it. The kids had a question. They were asking about bio. I don't know.
Yeah.
They were asking something about bio.
Happy birthday to you. Happy birthday to you. Happy birthday, dear
She wasn't paying attention. Thank you. That's nice. So the projectile in part B does feel air resistance. So we're going to look in this section we're going to look at symmetry a lot. And when air resistance is accounted for, we're going to lose that symmetry that we have. But without air resistance, the idealized motion or trajectory is following path A here, and we would see symmetry in the parabola. Just like in your math courses, when you graph parabolas, you have an axis of symmetry, and at the axis of symmetry is where the maximum height occurs, or with a parabola like this, is where the minimum occurs. The same is going to occur here in our projectile motion problems.
Does this only work for objects that are spherical or like?
Yeah, so the idea is that the shape of the object would affect air resistance.
Yeah.
So if we assume there's no air resistance, which we're going to do, the shape doesn't matter.
Okay.
But the closer it is to a sphere, or the closer it is to a streamlined shape, then it would have less air resistance. Yeah, but if you took a cube and tried to throw it, it would have a lot more air resistance. It would be tumbling at different angles. The air resistance would change as it changed its rotation, so there'd be a lot more to it.
Or if you take like a badminton.
Correct. Or like a beanbag or something like that. You throw it where it topples on itself or it rolls over.
If you like throw it and you had some like spin to it, is that gonna mess it up as well?
Yeah, so when you spin something, it gives it rotational energy. So some of the energy that goes into your throw will go into the spin. Now, the spin itself would definitely affect the amount of air resistance it feels as well. A bullet coming out of a barrel of a rifle, it actually rotates like this the whole way. So the shape of a bullet, say this is the bullet itself, it's a long bullet, right? But it rotates like this as it's spinning. The inside of the barrel of a rifle is rifled. That's why it's called a rifle. The inside of the barrel has cutouts in it that are actually making the bullet rotate like this. If the bullet weren't rotating like this, you wouldn't fire in a perfect line. That's why if you look at old movies, when they use muskets, what did muskets have? They didn't have bullets, they had musket balls. Yeah, they were literally like what we saw there. And those musket balls would just be launched out the end of the barrel. And the barrel, the inside, had a ton of impurities. There would be stuff in the inside of the barrel that wasn't smooth. So a musket being fired from here might end up there, might end up there. Like, it was never reliable, which is why in a lot of wars people end up like, yeah, you have to push it all the way down. But even when you did that still, the barrel on the inside was not smooth enough. So it would create impurities as it was being launched, or it would create defects in a sense. So you never had reliability. Now, obviously, with different types of weapons, it's different, yeah.
So the difference between A and B, so A, it's obviously the Y max value is higher, and the X because it'll travel further. But does A, like the force is greater because it goes further, or what's the difference between the two?
No. So in part B here, all that's happening is as it's traveling along the path, wind resistance is pushing in the leftward direction. So this projectile that wants to go this way is being pushed back slightly by air resistance, so it's not going to go as far in the X direction. It's also not going to make it as far up to max height as it would without air resistance.
So A is without air resistance, B is with air resistance.
Correct. B is with air resistance, A is without air resistance. Yep, very good. All right, so let's take a look at this, and let's take a look at an image so you can see what's physically happening. So this was exactly what we just did. Okay, this is literally what we just did. In the very beginning, this object was launched only with horizontal velocity. Only with horizontal velocity. And what we see at the very top here is that, look, our velocity is only VXO. Velocity in the horizontal with the O simply meaning initially. Velocity in the horizontal initially. And then what happens, as you notice, as I think Mauro mentioned, or I think it was Mauro that mentioned, we're adding velocity in the vertical direction. Now what's happening to the vector length? It's increasing. Because again, gravity is causing this object to accelerate toward the ground. And because it's accelerating, acceleration causes a change in velocity by definition. Acceleration is a change in velocity. So the Vy vector is increasing in length as this projectile falls toward the ground. What do you notice about the Vx vector? What do you notice about the Vx vector? It stays the same. Anybody think about why that is again? What did we just say? Why is the Vx vector not changing? Right, here it is. It's here again. Again, it's there. The Vx vector is just not changing. But Vy is. Again, what's that reasoning? What's that rationale? What's the rationale again? Come on, I'm seeing the same hands all the time. The same hands. George, help me out.
Because there's no acceleration on it.
Thank you. There's no acceleration in the x direction again. We're assuming no air resistance. Look at the acceleration in the diagram. It's given at the very top here. Acceleration is equal to g and it acts downward. You're told at the very top. So that's why the Vy component is consistently getting greater and greater in velocity. And take a look. This is our image. This is the one that was dropped. See it dropping? It's falling. it's falling, and look, they're falling at the exact same rate. This was what Nick just took a video of, literally happening until at the very end, these two projectiles both hit the ground at the exact same moment. Okay, what's the only major difference here? Is that one of them gains horizontal displacements. One of them, because it's launched this way, gains horizontal. The other does not gain any horizontal displacement because it was dropped. And look at the length of this vector here. The y velocity here is the exact same velocity as this velocity. So again, these two, let me point so you can see them. This velocity here and this velocity over here are the exact same value, these two right here. Over here, these velocities are the exact same two values. So as an object falls toward the ground, it doesn't matter what's happening to the x velocity. It means nothing to the y velocity. It means absolutely nothing. Okay, the y velocity changes only because of gravity. The x velocity does not impact the y velocity here. So when we look at these problems in this section, because the velocities don't affect each other, we are going to specifically look at the directions separately. We're going to look at the x direction, and we're going to look at the y direction, meaning the horizontal and the vertical motion in these problems. And we're going to separate them with one common trait. The common trait is time. Time is independent of direction. The time it takes this one to fall on the ground was the exact same time it takes this one to fall on the ground. So time is the variable that will be in both x and y directions. But beside that, we're going to look at the x equations on their own. We're going to look at the y equations on their own because they don't affect each other. Last thing about this image. Last thing. If I wanted to get the overall velocity at any moment, look at my diagrams here. The overall velocity is represented by this third vector at each location. See the angled vector at each location that I'm kind of highlighting or circling right now? All of those angled vectors, to get them, does anyone have any idea as to how we could calculate them? Or what are you thinking?
Find the x displacement and the y displacement, and then you use what you're learning from the vector.
Very, very close. Moro's exactly right, except he messed up one word. One word. He said you find the x displacement, you find the y displacement, and you use what we did with vectors to put them back together, which is right, but one word is not right there, Moro.
I was going to say something about angles.
He said displacement, right? And what was my question about? Velocity, my question was about. Remember I said, how are we going to calculate the overall velocity? Because think about it. If I'm traveling to the right and I'm traveling down at the same time, then I must have velocity at an angle. This is my overall velocity here. So for these problems, what we're going to do is we're going to notice that again, just like earlier with vectors, objects have x velocity, they have a y velocity, and then how are we going to get the overall velocity? What theorem are we going to use based on my diagram I just drew there? What theorem will it be? Pythagorean theorem. Okay, that will be the overall velocity. So we're going to see this happening a lot. We can say the following here. Okay? Vx squared plus Vy squared is equal to V squared. Again, this is Vx, this is Vy, and in red is V. That is going to happen a lot. And the other part we're going to notice is that we're also going to always be searching for an angle theta. And that angle theta will come about from this trig ratio. Oops, I'll actually just write it out the first time. Again, that's Vx, that's Vy, and that's V. So where do I get this ratio? Because it's opposite over adjacent. Vy over Vx. I'm putting absolute value here. We'll discuss more about why that is in a little bit. I don't want to get too far ahead of myself. Okay, I'm putting absolute value here for a reason. Okay, so throw that around your fraction, please. So we're going to be seeing this over and over. Let's take a look at one example to start. It'll help us to see an example first. So a bridge is 300 meters above a river. Tom Cruise jumps off the bridge to avoid a sticky situation he's gotten himself into. I'm thinking of like those Tom Cruise movies where he's like always Mission Impossible. He does all his own stunts. He jumps off the bridge by running off the edge in a horizontal direction. He does not leap. he just runs off the edge of the bridge. Like somebody's chasing him and he runs right off. Now, if he hits the surface of the water after a horizontal displacement of 50 meters, what is the velocity with which he jumped? Now, the first thing for all of these problems, the best thing you can do, think back to problem solving from last chapter. What did I mention you should start with? Start with always. Listing the givens. Very good. Now, in these problems, givens might be nice to draw in your diagram also. I would recommend that your givens, which is the first thing you do, actually show up in the diagram. So here's my diagram, and it's going to never change. My diagram will never change for these problems. For something from a cliff, or from a bridge, or from a building, here's my diagram. And that's it. And I make a point to say this is always my diagram because every problem in physics can be modeled. What do I mean by that? Well, we launched this projectile from here a moment ago, right? We launched it from here, and it fell toward the ground. It's the exact same thing as if Tom Cruise is running off of a bridge, and here's Tom Cruise, and he's running off of a bridge with velocity initially. And then Tom Cruise will follow this path toward his probably demise. No, he never dies actually, so he'll never die, yeah. Toward that location right there. And we know that this is 50 meters. That's a whole other thing, yes. Let's make believe he's not into Scientology anymore. I made these problems before, that was a big thing, I know. The bridge is 300 meters above the water level. So we label that in our diagram also. So here's my diagram, but you know what? Write yourself a note on the side. If a hunter shoots a bow and arrow, if another hunter shoots a rifle, if Morrow pitches a baseball, if, I'm just thinking of something that's a pitcher, like in general, all these situations are exactly this. Because if I launch a bow and arrow, if I throw a baseball, if I shoot a pellet from a gun or an actual bullet, what's going to happen? It's going to start at some height, and what is it going to do eventually? Where is it going to most likely end up? If it doesn't hit something, it's going to end up on the ground. Or maybe the catcher is here, right? Somebody throws a pitch, the catcher's waiting for the ball. Well, the ball started up here, right? The pitcher literally releases the ball here. And yet, the ball lands down here in the strike zone. So clearly, even with baseball, even with something you think has no drop to it, the ball or the object definitely drops. So I like to generalize all of these problems like this. This is my diagram. It looks like a cliff. There's no bridge here. That may be a little artistic part with the water, right? So you can see water, but it doesn't matter. I can put this as a straight line, and it's the same thing, water, ground, whatever. Maybe this is where the catcher is, and there's a person catching the ball. Who knows what it is? But the problem can always be modeled this way. So, for all horizontally fired projectiles, this is your diagram. Again, for all horizontally fired projectiles, you can use this diagram. And we model all of our problems this way, that are horizontally fired. Can somebody again explain what I mean when I say horizontally fired? I keep saying it on purpose because it's really important here. Horizontally fired. How can it be differently fired? How can the firing be different, Nick?
You can fire vertical and down.
If you fire vertically up, vertically down, very good. Or
It could just be dropped.
it could be dropped, good. Or it could be fired at an angle. All of those scenarios are different than the one we just stated. So what we're going to do is in this course, for the most part, is we're going to classify problems. We're going to categorize them so that we have a general consensus as to how to begin the problem every time. You want to have these what I call under your tool belt, right? Your tool belt of problems. This is one of the types of problems here that we're going to look at. Now, let's get back into the problem itself. The given information we've drawn on the diagram already. We're looking for V0. That's our unknown, our desired variable. What's the one other piece of info that I haven't drawn yet, but we do know for all of these problems?
The vertical acceleration is minus 9.181.
Very good. The acceleration in the y direction, is going to be negative 9.81. Now, by the way, this is trivial. Doesn't matter. I'm going to drop the 1 from 9.81 from now on. Only reason being, I didn't realize on your formula sheets it said 9.8. It doesn't use 9.81. When I was in high school, we used 9.81, which is more precise. But gravity has a tendency, books have a tendency to round gravity to 9.8, or 10 sometimes. 10 is only used on like the subject test for physics to make numbers easier, because there's no calculator allowed in the test. If you take the subject test in physics, the SAT one, you can't use the calculator on it. So they make gravity 10 for that reason. But so you're aware, I'm going to drop the one at the end from this point on. I didn't do it early enough, I apologize. Just bear with me with that, okay? That is the acceleration. And notice what I put here. What is that subscript? Can anybody, it's tough to read.
Why?
Why? Because I want the acceleration vertically. The acceleration vertically. What's the acceleration horizontally? What did we say for these problems? 0. We are assuming there's no air resistance. Okay? There's no air resistance. So, let's take a look at this problem now. We've got our diagram, that's the beginning part. That's probably the most important part. But now what we do is we create 2 columns. I have a tendency to make my x column not as wide as my y column because there's not as much math going on and lengthy equations. So I don't make it split down the middle. I usually put this over here. This is a great technique for organizing your equations. It really helps a lot, especially for those that like organizational tools. For those that struggled on the vector stuff, when you come see me, I'm going to show you a table method that I kind of went over in office hours because some really still struggled on the test. Not everybody, most did pretty well, but there were a select few that struggled with vectors. We'll do something like this with vectors in office hours to help you organize your ideas. So for this problem, what I want to do is I want to list the equations that I could use. Well, if you remember, we have 3 main equations. We have this one. I'm going to put them at the top. That's the first one. We've got this one next. And then we've got this one last. And these are all on your formula sheet. And by now, some of you probably have them memorized, some may not. Okay, at some point, I promise they will become memorized just inherently from doing enough problems. So those are my 3 equations. And those are the 3 equations we started with. If we're moving, though, in a vertical direction, instead of calling it x, I'm going to call it y. I'm going to call the variable y. So in the x and y direction, we have to think about what equations we could use. Well, people, in the x direction, what did we say was 0 in the x direction always? What was 0 in the x direction always? Acceleration. So take a look real quick. Drop this off. Drop this off. Drop this off. Because acceleration doesn't exist in the x direction for projectile problems. So tell me, which of these 3 equations is actually meaningful still? Which has some meaning to it, Juliet? The first one. Juliet, you want to answer the follow-up question? Why don't the second 2 have any meaning to them?
Because it's just like 2 variables, the velocity and the initial velocity.
So the initial velocity is equal to the final, or the velocity at other time. This tells me the initial velocity squared is equal to the velocity squared at some other time. Why are these equations absolutely correct but not useful? They're definitely correct. Why are they correct, and then why are they not useful?
Because there is going to be a change in the excuse me, sorry. Because, just because of the change in distance, there is going to be a change in velocity.
Careful. In the y direction, remember, velocity changes, we said. But what's the acceleration in the x direction?
0.
So if acceleration is 0, and acceleration is defined as the change in velocity, what can we conclude? Louder. There's no change in velocity in the x direction ever. Which is why these statements make sense, but they're kind of trivial. It's saying the velocity to start in the x direction equals the velocity at the end in the x direction, squared for both. Or the velocity in the beginning equals the velocity at the end. In the x direction, these are true. So in the x direction, we're only ever going to use this equation right here. Now, because I'm in the x direction, I like to use subscripts, and it will help. So instead of v0 here, let's call this v0x, or vx0. Your book does vx0, I do v0x. It doesn't make a difference. Okay? I'm going to put a little extra subscript, though, as an x there. Again, I'm putting an x right here to indicate the initial velocity in the x direction. Now, vertically, All three of those equations can be used. Because in the vertical direction, what do we have? What's that one word that we do have in the vertical? Acceleration. Yeah, acceleration. Only in the vertical direction, negative 9.8 meters per second squared. So what we can notice here is that we have a choice, right? We've got an option. Now, we've got an option, but our options are limited based on the givens. Based on the givens. So in the y direction, list your givens, please. List the given values you know in the y direction. And you can do that from your diagram to help you. But in the y, I didn't list them in the x direction because I'm always going to use this equation in the x direction. It's never going to change. So I didn't have to choose an equation. But because I have to choose one of those three equations in the y direction, I will start by listing what I know. So give me one piece of information that I do know in the y direction. One piece of information.
The initial height, so x is 0.
So what's the initial height? What are you going to call it?
0 and then negative 300.
Okay, so watch what Jack is doing. He's calling the starting point 0 and saying it's going to land 300 meters below. Anyone have another? It's correct. Anyone have another way we can write this? Janisi.
We can say y naught is 300 and y is 0.
So either way works, but you need to be consistent. Okay, so if you're going to use this arrangement, you need to use 0 and then negative 300. Or you could say it starts at 300 and it ends at 0. But in either problem, it won't matter. Because again, we have y and we have y0. Right? We've got y and y0 in both spots. Or here we have delta y, which is y minus y0. So either case, we're going to have this idea. And if I do y minus y0, it's going to be 0 minus 300, which is negative 300. Or negative 300 minus 0, which is still negative 300. So either you choose this way or you choose this way. I happen to choose, just so you know from my notes, when you do it later, I chose this way here. Where I started at a height of 300 and I ended what I'm calling the ground level. Okay, and I do that only because sometimes it's easier to think of the water level as sea level or ground level as 0. And then give this initial height of 300. But if you want to choose this way, it is absolutely fine, you can. There's nothing wrong with it. My question though now is this. What equation can I use, or what other information do I have or not have right now? What are my other givens? George?
Oh, you have acceleration at negative 9.8.
And what other piece of information? I've got one other piece. Maura?
What you don't have is final velocity.
We don't have final velocity. That's unknown, I agree. In the y direction and in the x both. Well, in the x we'll talk about. Justin? Horizontal displacement goes over here. Yep, I like that as 50. And the starting point was 0 for the horizontal. But what else in the y direction, Vin?
You know the initial velocity is 0.
Can you explain that, Vin?
Starting with the top point, like it's at the moment stop before the acceleration starts.
So what Vin is saying, if you think about a projectile when it's launched, when it gets to the very top, it stops until it starts to fall back down. So the problem that we're looking at right here, right, this launcher is launching only with x velocity. So it's like the second half of the parabola. Think about our problem here, right? This is the second half of the parabola. And as Vin noticed and mentioned, he said, well, at the apex, or at the max height, apex, max height, the object isn't moving vertically. It's only launched horizontally here to start. And then it starts to do what? Pick up vertical velocity on the way down. But to start, this is 0. Circle this, asterisk this, right here. This is the most important part for horizontally fired projectiles. V0 in the y direction is 0. Okay, that is huge. I don't know if you need to put stars around it or something, but please do it in your notes. That's so important. And this is always the case for an object that's starting at max height and moving like this, or just simply fired horizontally. Right? Starting at max height, if I drop it, or if it got up to max height and we start the problem from right here, and then it continues the rest of the way, this is true for those scenarios, or being launched horizontally. Now, with that said, our goal is to figure out the initial velocity in general, which we don't know. But I do know the fact that, hey, the velocity in the x direction is the initial velocity. That's what we're looking for in this problem. Our goal is to figure out how much is launched with in the x direction. So our goal is to figure out this quantity right here. So we need v0x really, which is what we're looking for in this equation right here. We've got x is 50. So take a look at the x for now. Please look up. Look at the x direction. This 50 goes in here. This 0 goes in here. This is what we're looking for, which is this variable right here. So if we're looking for this, then we've got this and we've got this, and we're looking for this again. What else do we still need? Time. So write this down in big letters. Time is your linking variable. Time is your linking variable. Because it links the x and y directions together. It links them together. And what I mean by that is we can now say, there's not much I can do in the x direction, unfortunately, because I have too many things unknown. I'm missing both v0 and t. Right? If I were to plug in, just so you can see what I have here, and I normally wouldn't plug in numbers, and we'll talk about that, why that is. Here's what I've got. That's the equation in the x direction. 50, right? 50 goes in for x, 0 goes in for x0, and I'm missing two variables. Two variables I cannot solve with only one equation. That's why you learn this in Algebra 2. So I need a system. I need a second equation to make this work. So I'm going to move into my y direction. Now in the y direction, I don't know velocity in the y direction at the end, and I don't know time. Those are both unknown. Both of these variables are unknown. Does the problem ask me about the velocity in the y direction? Do I need to figure it out? Does it say find the velocity at the end of the problem? Or find the velocity upon impact? It only asks for the velocity where? Where? At the?
Release, like when he jumps.
Yeah, when he jumps off the bridge. That's the only velocity we care about. So our problem is asking us for this right here. We don't care about this. It's not given, and we're not asked to find it. So, as a result, this is not important, which means we can rule out the bottom two equations already. Go back up to your three equations up top. I'm ruling out the bottom equations because, again, I'm not asked about the final velocity at all. I'm not asked about the velocity 5 seconds into the problem in the y direction. I'm asked about the velocity at the beginning, which is only in the x direction. So that means I only have one formula to choose. So I'm going to choose y equals y0 plus v0 yt plus 1/2 at squared. And I'm starting to use subscripts everywhere, if you notice. Subscript right here. Subscript right here. That's a sub y. This is v0 sub y. Okay, because it's the velocity initially in the y direction. The acceleration in the y direction. It's important to specify in these problems now. So what are some things we know? I'm going to use the approach, I'm going to cross this off, not to confuse anyone. I'm going to use the approach that we start at a height of 300 and end at a height of 0. So I can automatically already say that this is 0, and I can also say that this whole thing is 0 right here. Take a look at what I've crossed out. The final height is the ground, which is 0. The initial height, well, that's 300, so we're going to use it. The initial velocity, as Vinny told us a little while ago, is 0 in the y direction. Again, what we just put these stars around, because it's only fired horizontally. It's only fired horizontally. So that drops off. AY is negative 9.8. This is known. What's the only unknown in this equation that's left? What's the only unknown? Time, t. And then we'll plug it in over here and be able to get VOX. So, I want to point something out. Big, big, important thing. You can either plug in numbers now. You can plug in negative 9.81 or 9.8 and plug in 300 and solve for t and get a number and get the time. The problem doesn't ask me for time anyway. So I can also just solve this algebraically with variables and plug that expression in over here using substitution method. So watch what I'm going to do here. I'm going to write what it becomes. This equation becomes 0 equals y0 plus 1/2 ay t squared. That's what it becomes. And then if I solve this for time, I'm going to subtract y0 I'm showing the steps today. I'm not going to show these steps ever again. I'm then going to double to get rid of the 1/2. I'm then going to divide by A. And then finally, to get rid of the square, I'm going to take the... Yeah. And normally when I put a square root, what do? What do I put out in front of it? But do I have to here? Because time cannot be... Okay, so I don't care about that. So this is my answer for time. Sure, by all means, plug in. You will get... Of course, I didn't plug in to get it, because I didn't care about it as much. Yeah. So I didn't plug in my numbers. But if you want to know what the time is when it impacts the ground, plug in. -2 times 300 divided by -9.8. That number under the square root. You'll get a time. I don't care what that time is, though, because the problem doesn't ask me for time. So instead, what I do is this. I take this expression, and I plug it in right there. Because again, I'd rather solve with variables. So instead of 50, I'm going to make this back to x, so I have all variables. I'm going to call 50 x again. I'm going to cross this off, this 50, and put it back as an x. This equation then becomes x equals v0x times that whole quantity. And that's my equation. And what was my goal? My goal was to find v0x, the velocity in the x direction. So just divide by this giant square root looking thing here. Just divide by the square root, please. So this equation, as a final answer, becomes this. v0x equals x over that entire square root. This is my final answer. On a test, technically speaking, you get to this point, it's right. Now, if you plug a number in and you get a wrong answer, I might take off like a 1/4 point or 1/2 point. Now, a couple of you saw that on your test, this one, because you solved everything correctly and then somehow made a mistake in your calculator. If you can get to this point, you've done the problem. On an AP exam, a lot of problems don't give numbers. And they'll say, find the solution in terms of your other variables. This is velocity in terms of horizontal displacement, vertical starting position, and vertical acceleration. That's this answer. Velocity as a function of those three. Why am I pushing you to solve with variables, do you think? Before I get to the question. Why do you think I'm pushing you to solve with variables? What's the power to this solution method? It's powerful. It really is powerful. Why, Jack? What do you think?
Since you never round, it's like exactly
Correct. I didn't even think about that. Very good, Jack. We're not rounding time as a decimal, so the answer will be exactly correct. Very good. I didn't even think about that. There's a second reason to it. A second reason. Seb.
Is it repeatable for any question that's...
Seb, there it is. This solution is a generic solution for all problems that are launched horizontally when you're trying to find the launch velocity. This is a generic solution. So I could say now, ready? What if Tom Cruise lands 75 meters from where he started? Well, instead of putting a 50 here, what do you put in? 75. What if I make it even annoying like last time? What if gravity feels now air resistance and gravity is half of gravity? I change this instead of 9.8 or negative 9.8, I make it negative 4.9. What if I say the cliff height or the bridge is not 300 meters, but 500 meters? Now y0 becomes 500. Do you see what I mean? How I can now vary all of these things, which means we call them parameters. X, y0, ay are parameters. We can vary those parameters and get different results. Would you do this by hand? Probably not. You would use a computer program, and you would write a conditional statement, and you would use loops, and you would use what are called vectors. And those vectors, or they're called arrays in computers, you would consistently change one of the variables. Then you would run it through the calculator program, and it would spit out 6 different initial velocities based on the 6 different x values, or changing each one. The number this turns out to be is 6.4. Okay, 6.4 meters per second. What you're going to notice is that at the end of the notes, we're not even close to done, but at the end of the notes, your homework has 2 types of problems. The ones that don't have the asterisks, you can start tonight. Okay, you can definitely start the ones without the asterisk. I've already put it up on Moodle as well. Again, tomorrow and Wednesday after school office hours, please. If for some reason your project reading part isn't in, and it's not in still today, it's already late 2 days, get it in today, or you're going to lose a lot more than you'd want to on a project read. I suspect everyone's is in, but I'm just saying that in case. So the second example says, we've got this plane, it's like a fighter jet, and it's flying 500 meters above the ground. It needs to drop a package to soldiers on a remote island. So it's flying like this, right? It wants to drop this package so that it lands on the island. It says the velocity of the plane is given in kilometers per hour, which I've converted to meters per second for you, when it drops the package. How long does it take for the package to reach the ground? And how far will it travel horizontally before it reaches the island? So here's what I want to do first to see this, or to show this. Some students don't really right away recognize why this is a horizontally fired projectile problem. And let me go through it with you. So remember last class I said I'm always going to draw a cliff? Right? I'm always going to draw a cliff when it's fired horizontally like that from a given height. So watch this. Here's the plane. The marker is the package. Okay? The plane is the eraser. The plane is going, it's going, it's going, it's going, and it drops the package. And it sounds kind of ridiculous to think about that, but a minute, look at it and try to visualize it in slow motion. As it falls, I was on slow motion, we drop the package, and the package falls like, well, the package technically falls like this, underneath the plane the entire time. And it stays right underneath the plane. It's hard to see it. You can maybe video it and you can do slow motion again if you want to. But if you try to look closely, the marker will move with the eraser. It will always stay below the eraser as it's dropped. So the velocity of the plane that it's moving with is the same as the velocity of this as it drops. It's going to be tough. I'm going to be moving. Ready?
Yeah, I'll go over here.
Yeah. I'm going to try to get it. I'll drop it, try to do it in front of you. Ready? Did you get it on the screen or not?
Yeah, it's good.
Okay. The idea, though, again, is that if you were in a car and you jumped out the door of the car, you would be moving with the velocity with which the car is traveling. Right? Have you ever seen those movies where somebody like jumps out of a car and they tuck and roll and they're like, oh, they're okay? No, you would not be okay. Okay? If you're driving a car that's going like 60 and you literally open the door and jump out, you would be moving at 60 miles an hour and you would like tumble down the road and you get road rash and you get cut, you might kill yourself in the end. But what I'm getting at, not the point, what I'm getting at, more than road rash, yeah. Yeah, probably fractures and head injuries and TBIs, all that. But the idea is that if you're in a moving vehicle, you're moving with the same velocity as that moving vehicle. So when this package is dropped, it's moving with initial velocity in the x direction. Because the plane is only flying in the x direction right now. It's not flying up, it's not flying down. It's flying horizontally, and then it drops the package. So let's say again, this speed is 186 meters per second. When it drops the package will be moving in this direction with a velocity of 186 meters per second. And it'll keep moving with that velocity, which is why the package stays directly below the plane. Even after it's dropped, it's going to move directly below the plane. What am I assuming we are not accounting for again? Air resistance, because that would change the ballgame completely, okay? Julia, sorry.
This sort of has to do with
It's
this,
okay.
but in my driver's ed class, they were talking about like when you're in a car and the car crashes, if you like don't have your seatbelt on, you'll go through the windshield because you're moving like at the same velocity.
It's exactly right, yep. And we're going to go into that exact thing, actually, when we get to collisions and impulse and momentum. But the idea behind that is exactly right. When you don't wear a seatbelt, you're moving at the velocity of the car. Well, if the car suddenly stops, you're not going to stop. That's why people literally get thrown through a windshield if they're not having their seatbelt on. So when you drive or when you're in a car, make sure to have your seatbelt on for not just that reason, but for other safety reasons in case anything else happens. But for collisions especially, that will happen, yeah? So again, the idea I want you to think about, and if you want to draw it for yourself here, go ahead and draw a picture of this so you can see it. So here's the plane, and here's the package. Then here's the plane, and then here's the package. Then here's the plane, and then here's the package again. So as the plane continues to move forward after the package has been dropped, the package follows this parabolic path, right? This curved parabolic path. And the package itself keeps accelerating downward because of what again? Gravity. But it doesn't accelerate left to right. It doesn't accelerate or decelerate, I should say, left to right. The assumption is that there's no air resistance. So the package will continue to move with the same horizontal velocity that the plane is moving with. So if you recall from yesterday, I drew these vectors. Well, it's the same exact setup again. Here's the package, and it's moving with the same horizontal velocity. It's increasing in its vertical velocity. And by increasing, I mean increasing in the negative direction. Okay? This is a diagram that you should have, like, not memorized, but understood. Yeah, you can memorize it, obviously, but understand what it means. Vx is not changing because my x vector is never changing. My Vy, though, is becoming more and more and more and more negative as this package falls to the ground. So, in this section, in this topic, in this idea, we keep recognizing that we need to look at our x and our y directions separately. We have to look at them separately. Which is why when you're in a car, have you ever tossed an object up and down when you're in the car moving? It doesn't come back and smack you in the face, right? It doesn't do that. You toss it straight up, it comes straight back down. Yet the car is moving. So one would think, when I was a kid, I used to think this, right? You throw a ball up in the air, if the car's moving, the ball's going to come backwards and hit you. And you see it in like old, what are they called? Acme, the Bugs Bunny and those kind of things, you know? The cartoons. Roadrunner, Coyote, all those ridiculous ones where the coyote runs off the cliff and he like stops and realizes he's off the cliff and then he starts to fall.
They move the hole.
Yeah, yeah, exactly. Something changes. So if you toss an object in a car, why doesn't it come back and hit you in the face? Why not?
The ball is actually moving as fast as the car is.
The ball itself, remember we just said, if I drop this package, the package is moving horizontally with the same velocity as the plane. When you toss the ball up in the air, you're giving it what kind of velocity? When you toss it up? Vertical. Well, you know what? It's already got horizontal velocity. It's got the same horizontal velocity that you have. Now, technically speaking, if somehow you could toss it up in the air, slam on the brakes of the car at the same time, then you have a bit of a situation. You know that happens. Because when you're on the train or in a car, you hit the brakes, what happens? Where do you go? Oh, backward is the accelerator. When you hit the gas and you accelerate forward, you get that push back. But when you hit the brakes, you fly forward. And that's more of inertia we're going to talk about in the next section, but the idea carries over to this method here. So when I toss an object up in the air, even though I'm tossing it up in the air, if I'm moving as I'm walking and I toss it up, it moves with me. Right? It moves with me. So when I'm tossing it, because I have some velocity and the marker has velocity, it moves in this parabolic path. And it comes back down into my hand. That's what just happened right now. Any good footage for that at all? Can you see if they're like separate or not?
I should do it again.
Don't even worry about it. Well, I'll pull up a video. We'll see. We'll take a look at it. I just wanted to see if that worked.
If you're in like a convertible, I know this is a specific example, but if you throw it up and the ball goes.
Yeah, so in a convertible, because there's air resistance outside of the car, if you tossed it up and it exceeded the height of your windshield where the air was coming over, it would definitely get launched backward. Yep. Very, very good, yeah. The same goes for, I'll show you a video actually. Let me show you a video real quick. I can probably airdrop it. I saved this video the other day. Let me just pull up what the account is. Yeah. For collision, say again?
For collisions, if you hit something, you get launched back.
Depends on the type of collision, yes, but it depends on the type of collision. Yeah, so I mean, like they're called elastic versus inelastic, and we're gonna get into those types. But yeah, sometimes you rebound off.
Now there was one in front of my building yesterday, and the whole car and then like a light bulb.
Oh, wrapped around.
And
It like melded around the car. Yeah, that's an inelastic collision where you get.
Back 5 feet.
Yeah, it's a wraparound. I know exactly what you're talking about. All right, let me pull this up so you guys can see it. While you're waiting for me to put this video up, I'm going to show a quick video of something. It's like a short clip. Start listing your givens. Look at your x direction. Look at your y direction. Try to write down what you know already. Nice. That's a great point. You heard Julie just said it's a great point. The guy that was sitting up top, if he tried to push the guy back in and was falling back, he'd get pushed back if he wasn't strapped in or holding in. Because every force has an equal opposite reaction. We're going to see that in Newton's law in the next chapter. But yeah, very good. Good point. All right, let's list what we know. Give me some information, please. What do we know? Christina, go ahead. I like that. So right away, the initial height is 500 meters. That's y0. and the final height it lands with is 0 meters. Again, like yesterday we talked about, you could call the initial height 0, and then the final height would be negative 500. It's up to you to decide what the starting value is. It's up to you to decide. And what Mr. Donachek likes to do, and I think it's a great method, I really do. He showed me this the other day. He likes to put an XY axis wherever his beginning of the problem is. So he does this when he starts problems. He'll start by putting an XY axis through the very beginning to show that that is the origin, so that he knows when he's looking at his problem later that his Y value that it started with was at the origin. So he does this, and then he does it falls to the ground. So in my case, can I leave this up here based on what I've written? Can I leave my XY axis up there? Where should mine be?
It should be at 500 and then over, we don't know how much.
We don't know how much over there, but the origin, you're close, but
The origin is where it hits the ground.
where it starts, where you want to consider the starting point, the origin. Based on our numbers, based on our numbers, where should I put my XY axis? He likes to start with it on the particle. 500 meters what?
Down.
Okay, so here is what you're saying, right? Yeah. Why, Seb? How come here's where it should be?
Because it's the height of that's the height of the plane above the ground. Yeah, I don't know.
Okay, now the initial height is above the origin, right? What did we say? We said the initial height, Christina says, the initial height is 500. So if I'm going to draw an XY axis in this diagram, the way I want to draw it is as follows. I want to take this XY axis and put it at the very bottom where it's going to hit the ground. So here's the ground right here. So the XY axis for me should really be right there. Okay, and let me discuss that one more time to show you what I mean. So in the Y direction, this object starts above ground level according to our value of Y0. So the origin has to be down here so that the object is somewhere above the origin. Then in the X direction, I'm going to start with this as my X0 position. I'm going to say that this object starts right here. So on the X-axis, it's at 0. On the Y-axis, it's at 500. So already I can write down that X0 is going to be 0 for this problem. And again, all that matters is the delta. The change in Y is what matters. So if you go ahead and use 0 and negative 500, that is absolutely fine. Here, you could call your starting X value whatever you want. If I started and I put my XY axis over here, let's make believe it's all the way over here, okay? If I did that, then it would be starting at some X0 value. And then we'd have to figure out what the X value is at the end and subtract these two numbers to get the differential. But I'd rather start with the X value of being 0 to start, because then whatever my answer is how far this object has traveled horizontally. So I'm going to call that the origin to start. What other information do we know in this problem? What other givens are there? Yeah.
The initial horizontal velocity is 186 meters per second.
Very good and well stated. The initial horizontal velocity. Initial horizontal velocity. Juliet.
The acceleration of the vertical is -9.8.
Very good. The acceleration, fine. The acceleration vertically is negative 9.8 meters per second squared. Very good. And vertically is the key word there. Then.
I would say that the acceleration horizontally is 0.
Very good. The acceleration horizontally is 0. Is 0. In today's simulation you're going to do afterward, we're going to turn air resistance on. And that would be just thinking of AX as some negative quantity. Imagine acceleration or air resistance is just pushing against your motion. So if you're falling this way, air resistance is going to push against you, and it's technically going to push up. And we'll see how that vector changes in the simulation. It's really useful. Let's see. Yeah.
You can say that Vx equals Vox.
Yeah, so we could also say this. Take a look at what Morrow's saying. He's saying we could call Vox just V bar x or Vx because it's a constant. It's not changing. So we could add this term in right here saying that, hey, this is always going to be the horizontal velocity. No matter where we are in the diagram, it's never changing from 186. Nice, good idea. One more piece of information is needed. What's the last given that we haven't listed yet? It's a given still. Isabella?
The vertical velocity is 0 meters per second.
The vertical, careful, initial velocity. Yep, initial, because it's not going to be 0 the whole time. Initially, the vertical velocity is 0, because this object, as the plane is moving, is dropped. Literally, dropped. And you can see it in this problem, right? My arm is the plane now, and here's the actual package. It's physically just released. That's all that happens in this problem. In the last one, Tom Cruise ran off the bridge, so it was a little bit tough to recognize that he didn't have any vertical velocity, but it's because he ran off horizontally. If he had jumped at an angle, then he would have had vertical and horizontal velocity. Okay, but for today, for this problem, this object only has horizontal velocity to begin. All right, so what are we trying to figure out? That's the next question, right? What are we figuring out? What are we figuring out? What's that?
The horizontal final position.
Very good. The horizontal final position is one thing we're looking for. That's one thing we're looking for, right? This problem has two things we're looking for. And the second is, and the second is, and the second is, Justin? Time. And just so you know, a lot of problems involve time. So although a problem might not ask you for time, you might inherently need to solve for time. Again, if a problem doesn't ask you for time, it doesn't mean you don't have to still figure out time. For example, if you look back at the last problem we did yesterday or 2 days ago, that was exactly that situation. Okay, the situation we looked at was, we need to figure out the time in the y direction in order to use it in the x direction. But that problem, if you recall, never asked us to figure out the time. It never said, how long does it take before Tom Cruise hits the water? It never said that. All it said was, with what velocity must he jump or run off the bridge to reach a certain horizontal displacement. Maybe, have you ever done this? Anybody ever jump off of a cliff or a waterfall? Okay, if you've done it before, you'll know that you need to jump outward, right? So you don't hit the rocks that are behind you. Now, below the water, there's also some that jut out. So you really need to push yourself outward. That was the Tom Cruise example. He needed to cover 50 meters. That was a pretty long distance, actually, horizontally. 50 meters, like half a football field. So he jumped a lot. Yeah, I know, think about that. He really jumped. He's Tom Cruise, though, so he can do it. But in this problem, we're going to notice here that we need to find time because we're asked, how long will it take? Why might time be important? Why might time be important in a problem like this, George?
Because it's the only way they can link the two equations.
Yeah, we're not going to be able to figure out x here unless we know time in the y direction. In the last problem, we had to solve for v0x, and we had x. Well, now we have v0x, and we're missing x. But it's the same analysis. We're using the same equation here, and on this side, we use, again, the same equation that we started with last time. So let's look at this problem over here. So let's say to ourselves, okay, in the x direction, the equation we're going to use every time is going to be this. Okay, it's never going to change in the x direction because we're not going to have acceleration in the x direction. In AP Physics next year, we'll talk about when we do have acceleration here and how it changes things. But this is going to be our equation. We don't have to put the plus 1/2 at squared because a is 0. There's no need to put the 1/2 at squared here because a is 0. Then,
Get rid of the XO.
and XO we can drop off. Yeah, good point. XO for the most part is always going to be 0. There might be some problems where you might be given a statement that says the particle starts at a position of 2 meters on the x. So that may not be 0 at times, but yes, in this problem it is definitely 0. Absolutely. Okay, so that drops off. So this is just our equation now, right? That's where we're left with here. In the y direction, we're going to use the same equation as last class. Why aren't we going to use the other two? Remember the other two. V equals v naught plus at. V squared equals v naught squared plus 2a delta y. Why aren't we going to use those other two equations is my question. Jack, what do you think?
Because we don't know final vertical velocity.
We don't know anything about the final velocity. Very good. We know initial velocity. We know our delta y value. We know acceleration. But we don't know our final velocity. So we'd have to solve for it in one equation, plug it into the other to then get time. We have to do two equations is what I'm saying. And I don't want to do two equations. I want to do only one when I can. So instead I'm going to use this equation. Sorry, on my screen I'm out of room. I know it shows up there. T squared. Okay, that's my equation I want to use in the y direction. Now, obviously, in the y direction, for horizontally fired projectiles, this drops off. It's not always going to happen. Okay, again, this in the next example, in our next class, not today, in our next class, this will not drop off because it will be fired at an angle and it will have some velocity in the y direction to start. Okay, but these ones, where they're starting fired horizontally, which is what this is modeled as. By the way, again, my cliff I didn't draw. Oh, I should draw my cliff. Remember I said you can always draw a cliff for these problems? Well, there's the cliff. Right? It's literally that same problem. Sure, I know the airplane isn't going to be riding along the cliff, but that's how I visualize this. I think of it as an object being kicked off of the cliff horizontally. So in the y direction, I can solve for time again. Because in example 1, I already solved for t, I don't need to go through the process again. I could simply write, oh, you know what? This value was 0 here. That drops off. It's going to be negative 2y0 over ay under the square root. And how do I know that? Because I just solved for it. Now, just solved for it in the last class. But I just did this earlier. We just did this in example number 1. So there's no need to go through the process of resolving for t when you know the generic solution will always be this whenever v0 is 0. And whenever this drops off, this will be our generic solution here. Now, both of these drop off, obviously. But this is not as important as this piece dropping off. Because what does this do? This removes t as a variable. Why is that important? Why does that matter that this t is no longer in the problem? Maura, what are you thinking?
Because then you don't have to use like the quadratic formula.
Exactly. If this time didn't drop off, you'd have t squared, you'd have t, and you'd have a constant. You would absolutely have to solve this with the quadratic formula, or on a graphing calculator, or the quadratic program, or with completing the square, or with intersection method, or with root method, whatever method you want to choose, you have to go through that process. But we don't have to right now, because that drops off. So go ahead and figure out what the time is, because we need the time in this problem. It asked us to find out time. What do we get for time? What do we get for time? Vin, what do you got? That sounds about right, Vin. I got, yep. And if I'm rounding, I put 10.1. That sounds right, rounding-wise, yep. So around 10 seconds, about 10 seconds later, it's going to hit the island. So, are the pilots going to be like, oh, you know what? I'm almost 10 seconds away, let's drop it. They're not going to use time. What are they going to use instead? Jack? Yeah, how far away? So what do we need to find next? X. The goal in this problem is to find X so that the pilots know when to drop the package. When they are 500 meters out of the island. When they're 200 meters away from the island. It's the distance away from the island that matters more horizontally than the time period. The time period is important, sure, but the pilot's not going to know when they're 10 seconds out of the island. They're not going to know, oh, based on my current velocity, we're 10 seconds out, okay, fire. It's not going to happen. They would know a distance because of the GPS that they're really using.
Instead of like finding 10.1 seconds, can you just plug that equation straight into the t on the other side?
Same as last time, but because this problem said how long will it take to reach the ground, I found out time in this problem. But yes, George, just like last problem, you can algebraically, generically sub in for t right here with this expression. Now, I'm going to point something else out real quick. You can also, if you want to, and I'm just putting these options out there, you don't have to, you could plug into that equation. You could just say 0 equals 500 plus 1/2 negative 9.8 times t squared. I'm running out of room. Times t squared over here. Okay, so you could do that. You could plug in at this point where it's written in red and then solve that for time, if you feel more comfortable. If you're really struggling to get the solution algebraically like this, by moving over y0, multiplying by 2 to get rid of the 1/2, dividing by ay, and then square rooting it, you could plug in at this moment, meaning here, and then solve this equation for time. Does that make sense what I'm saying? So whatever method you want to choose is up to you. Here's my approach, or here's my mental, or here's my understanding, right? This is if your math skills are really a little bit lower and you're struggling to get a generic solution. Getting a number first is the secondary one. You don't want to deal with moving this over and out algebraically because it could cause some error. Then if you're really confident, you should be taking this whole expression and plugging it in for time. So think about where you are as a student. Think about where you've gone or how you've done the first quarter and going forward what you want to take as an approach. But again, that's my methodology I would go about. So in this one I would say x equals v0x times square root negative 2y0 over ay. Okay, so I'm going to do exactly that. I'm going to take, just as George asked, I'm going to take this expression and plug it in for t. Again, for this specific problem, by all means, just take the 10.1 and plug it in. It's probably even easier, right? But I like to see powerful solutions. And I don't physically mean powerful. I mean, they can do a lot. I can now say, this plane, imagine, is now at 1,000 meters, not 500. What changes? Just that variable right there. Or, suddenly, the plane slows down before it drops the package. And the velocity of the plane is now 150 meters per second. It just changes that number right there. Hypothetically, air resistance is taken into account, and suddenly gravity affects it differently, and gravity is 8.2 instead of 9.8. It changes AY to 8.2. You follow what I'm saying? Again, I can parameterize this. I can sit here and say, the things that might vary are Y0, A, and V0. Those things may vary, so I like to have them in my answer for the final solution I'm looking for.
This is just a general question. Is there like a particular value that air resistance tends to?
There's not, and we're going to talk about that actually today in that that lab you guys are going to start with. Air resistance is a function of several things, and we'll go over what they are. You're going to see it in the lab, we'll go over that exact thing, okay? But it's not a certain value, unfortunately. Okay, so let's plug in those values. We've got x equals, and again, watch what I'm going to do. I'm going to put the 186 here, and then I'll just put the 10.1 here. But at least I know that if I wanted to go back and reevaluate this problem, I could simply change the y or the AY or the V0. But again, this is what it becomes. 186 times time, which was 10.1. Okay, that'll give me the horizontal range of this projectile. By the way, that's a word that's used widely in physics that can be very confusing. Range in physics means the horizontal displacement. Write that down. It's not like domain and range in math. Remember in math that your domain is your x values that the function can take on. The range are the y values or the dependent variable values. Here though, range is not vertical. Range is not vertical. Range is not vertical. When we say range in physics, we mean the range of the projectile. So if you were punting a football, and you were watching Monday Night Football this week, and you watch a punt, you have max height. That's how far they want to get the ball in the air, which is the goal of the punter, to get it really high up in the air, so you have hang time. And then the other goal of the punter is to punt it downfield to get maximum range. So range is the horizontal displacement, max height is the vertical displacement for a projectile being launched. Okay, good vocab for these words. The number is 1877.9, and I used 10.1 seconds. Vin, what was it? It was like 10.09 though, right? Something like that, the actual time? 0.96. So, this is something to talk about because we haven't really addressed this topic yet. You need to consider rounding later in the problem. So because I was asked to find time, I plugged in 10.1. But really, the better solution would be not to round at all and to carry all the decimals here into this value. And it might change this in a small way. Can you check that for me, Vin? You have the exact number in your calculator we had earlier? Keep all those decimals and then just multiply by 186.
So I got 1,086 and 925.
So it only changes by a 2.5 at the end here. So it's an additional 2/100ths of a meter that it would be different by. Okay, 2/100ths of a meter. So realistically in this problem, not as big of a deal, right? But for problems that involve square roots and squaring, this one did have square root though, but square roots and squaring as a secondary step, it will definitely be what's called a propagated error. Propagation of error is like, I round earlier, and then I use that number here. Then I round that number, and I use it later. Then I round that number, and I use it later. Do you guys notice on your grade book online, I don't ever round your grades. Did you notice that by now? Like I don't, when you put your test scores in, I put in like, out of 60 points, 51.5, 51.25. I don't ever round your grades because I know math better. If I rounded every grade, it could hurt or help you. And it really would. And I remember in middle school that I actually proved to my teacher that my grade would have been like a point. I know this is ridiculous, ignorant, whatever. My grade would have been like a point or two higher had this teacher not rounded throughout the entire year with every grade. So when you get a raw score in a class, and you get that raw score, you could say, oh, you know, a 52.5 out of 60 might be, I don't know what that is, 52.5, I pick that number to use. So I say 48.5 out of 60 would be around an 80, because 48 out of 60 is an 80. So 48.5, I should not round that to an 80, even though it's an 80.4. I should leave it as 48.5 out of 60. Do you follow what I'm saying? If you keep rounding, that error gets worse and worse and worse. So in physics, if you use the generic solution and plug in all variables, you never have to round, because these numbers are not rounded. So that's why this solution is also more powerful than getting a number first and then plugging that number in here. More.
I was just gonna say, I rounded to 3.1, but I got 1878.6.
Yeah.
You got 1878.6 when you rounded to 10.1? Thank you. So I must have not rounded when I did my calculation. You see the difference? So this is using this right here, and this is using this right here. Thank you, Mauro. So it turned out that, Vin, I got your answer and I ended up rounding that answer, it looks like, the exact value. But if you did use 10.1 with this number, this is the number that you're getting. I mean, we're off by a solid meter. Now, for the purpose of this problem, it doesn't matter much because the island has some width to it, right? The island has width. If the island had a certain, it was not a point in space, you don't have to hit it exactly. If you're off by a meter, it's not the end of the world. Now, it is the end of the world if you're dropping something like a package that could hurt people, or if you're dropping something hypothetically that needs to be caught by someone, or whatever the scenario may be. The apparatus needs to land perfectly, and it's off suddenly by a meter. Okay, by a meter. That could have a big impact. All right. So at this point, I want to pause. So in this slide, what we were talking about was the idea that you guys all saw in your lab now, that when an object is fired at an angle, it's got both x and y velocity. The nice thing about this chapter is that we don't need any new vector ideas. We're using the same vector ideas we learned earlier. When you want the x component of a vector, we multiply it by the cosine of theta. When you want the y component of a vector, we multiply it by the sine of theta. So depending upon what we're doing, when we're looking at directionally, we're either going to use v0 cos theta or v0 sine theta to give us the starting velocities in this problem. And the same goes for the ending velocities. If we have vx at the end and we have vy at the end, we can find the overall velocity using what theorem? Hello, what theorem? Pythagorean theorem at the end there. Okay? Same as we did with the horizontally fired projectiles there. So let's jump right into this example. So back to Tom Cruise. Tom Cruise strikes again in a new action movie. He has to leap from the top of one building to another. The second building is 4 meters away from and 2 meters or 2.5 meters below the other building. So 4 meters away and 2.5 meters below. So stop right there and draw me a diagram. What do you perceive this to be? Because some of these problems, the hardest part is the diagram and the knowns and the givens. So starting with only the first 3 sentences, first one doesn't matter, the first 3 sentences, draw yourself a diagram only. I don't care about the other stuff after. So just the diagram of the arrangement. Give you about 20 to 30 seconds most, because you should be able to figure the diagram out pretty quick. Keywords. 4 meters away, 2.5 meters below. When I hear 4 meters away, it doesn't tell me that much yet. At first I'm like, does away from something mean vertically or horizontally? I don't really know. The word away doesn't help me much. But after that, I notice it says 2.5 meters below the other building, right? So if it's 2.5 meters below the first building to the second, what must away represent in this case? What must it represent? Very good. The horizontal displacement. So the first building is here. The second building is right here. And notice the way I've drawn this. Again, the second building is 2.5 meters below. And the second building is 4 meters away from the first building. So if the word away confused you, which it could, I can see that being confusing because it doesn't say horizontally or vertically for the word away. Bless you. The vertical value helps us a lot more here because the vertical value gives us that we know, oh, that's delta y. So that 4 meters must be delta x. So this is my diagram to start. Okay, and notice on the diagram I use double-ended arrows. Okay, and in physics, double-ended arrows don't necessarily mean a line. Okay, they actually mean like a line segment. So this is the gap here, and that's the gap right there. Next, it says that he gets a running start, and Tom Cruise jumps off the edge of the building at an angle of 15 degrees. So let's draw Tom Cruise, and there he is. Let's draw an angle of 15 degrees. I'm going to try to draw things to scale as best I can. Again, theta, it's hard to squeeze that number in, so I'm going to just put theta, and then I'm going to put it over here. In V0, it says, while traveling at a velocity, again, of 5 meters per second. Or not again, sorry, last problem we found the velocity. So that's the velocity he's running at. He jumps off the end. This is just like a long jump problem. For anybody that's in track and field, this is literally the long jump problem. You want to propel yourself forward, except in the long jump, you land at the same altitude you started. Here we're landing below where we started. So, if I start looking at this, the question says, will he make it to the other rooftop? Will he make it to the other rooftop? Will he make it to the rooftop? It's a loaded question, because I'm given a lot of information in this problem. One might say I'm giving too much information in this problem, actually. One might say I'm giving too much information in this problem. Why might I be giving too much information? What do I mean by that statement? Jack, what do you think?
Maybe because we have all our variables that we need to solve it, so you just plug it in.
Maybe, okay.
You don't need everything that you're given.
Maybe you don't need anything given. Do you know what you wouldn't be needing here? You might know what you maybe wouldn't be needing, Francisco? Say again? We don't really need the 4 meters. What do you mean by that, Francisco?
Because you have this horizontal velocity.
He's on the right track. He's saying if we have the velocity, we can find out the horizontal velocity, and we don't really need the 4 meters. Why don't we need the 4 meters? I can say we don't need the 4 meters, or we don't need the 2.5, but we don't need one of them. I'll tell you that much. We don't need one of them.
I was gonna say you don't really need the 2.5 because
That works, okay?
technically if you did if you had a parabola, you would know that you were gonna, and you cleared the 4 meters, you would know you're gonna land in the vertical area of this is not very physics, but you're gonna land in the vertical area of the other building.
I like what you're saying, the vertical plane.
Yeah, so you're gonna
Where you would cross the plane is what you're saying. So let's take a look at both approaches. So I'm going to start with Francisco's approach. Ready? Francisco said the following. We don't need the 4 meter mark. And here's what he's saying. We can instead say, oh, you know what? X is unknown in this problem. We could start by saying that. And we could say, you know what? When Tom Cruise falls 2.5 meters, where will he be horizontally? If he's less than 4 meters, right? So here's the trajectory. I'll actually do it on the board so you can see it better. So Tom Cruise might take this path. And after 2.5 meters of falling, maybe he's right there. Does he make it? He doesn't make it, right? Or maybe after 2.5 meters of falling, he's right there. In that case, he would make it, right? So what we could do is we could set y0 equal to 2.5. We could set y final equal to 0 and solve for x. And if x is less than 4, he doesn't make it. If x is more than 4, he does make it. So the first way to solve this problem is what Francisco said and say, we don't need the x displacement. And we can solve for the x displacement and see if it's more or less than 4 meters. If it's more than 4 meters, he clears it. If it's less, he doesn't. Well, how are we going to get the x displacement? We're going to have to get time from the y direction, and that's using a delta y of negative 2.5. Then, we could also instead say, maybe we do know the x value. We do know it, and maybe we don't know what y is equal to then. Well, if I set x equal to 4 meters, what I can do is I could say, well, is he going to be here after 4 meters? Or if we continue going down, he would be considered down here after 4 meters. So we could set x equal to 4 meters and determine our delta y. If our delta y is more than negative 2.5, say delta y turns out to be negative 4.5. It means after 4 meters this way, he has fallen 4.5 meters this way, and he wouldn't make the jump. But after 4 meters horizontally, maybe his delta y is only negative 0.5 meters. So we started here, negative 0.5 meters would be like right there. Negative 2.5 meters if it turns out to mean he would just grab the ledge or just land on the ledge. So we could either let x be 4 and find y, or let y be negative 2.5 and find x. But either scenario will yield the same solution. Either he makes it or he doesn't make it. Okay, so for today, for the purpose of our time, because we don't have much left, here's what I'd like you to start thinking about. You guys have 2 nights, okay? I want you to, this half of the room, follow what I'm doing, this half of the room, okay, so jot this down, this half of the room. Let x equal 4 and solve for delta y. See how much he falls. Let x equal 4 and solve for delta y. This half of the room, let y equal delta y. Sorry, let delta y equal negative 2.5 for this half of the room. Let delta y equal negative 2.5 and solve for x. I want to approach this problem 2 different ways so you guys can see the idea that sometimes in these problems you can take one route or another. So you have 2 nights. You have 2 nights. I recommend that you start it. I also recommend, because I didn't do the homework on this section yet at an angle, that you maybe go back and look at the problem set questions for horizontally fired to get a head start. Okay? You don't have to elaborate on what we did today. Nothing to turn in. So over the next 2 days, just look at this problem alone and the problem set for horizontally fired projectiles. And you can always start thinking about your project also. That's another thing to keep in the back of your mind.
Oh, yeah.
Oh, Jack. Because then you have to find the center of that building and say, this is a position of, say, 8 meters, but there's 8 meters long, and you want to 7 meters. It's a range of solutions. Here the range is x needs to be greater than 4. If it's greater than 4, anything greater than 4 is a land. Anything less than 4 is a land. That's in the range in this case. I'll talk to you more about this next time, okay? You're welcome, guys. Have a good day. Let's take a look. Come on. So let's take a look at this one now. So we want to figure out whether Tom Cruise makes the jump or not. So let's start by looking at the method where we're going to look or search for y, and we're going to let x equal 4. Okay, so this first method, we're going to say x is equal to 4. Let's figure out what the y value is. If he drops more than 2.5 meters after he's traveled 4 meters this way, then he's not going to make it. If he drops less than 2.5 meters, then he will make it. If he drops exactly 2.5 meters, he'll just catch the edge of the next building. Okay, and again, we're modeling the person as a point in space, when in reality the person has height, right? Has some dimension to him or her. So because we want to figure this part out by letting x equal 4, we could start by looking at our x direction. So in our x direction, let's take a look at what we've got going on here. We've got x equal to 4 meters. We've got v0x equal to 5 cosine 15. And where is that coming from, that part right there? This is the new part that we're looking at now. 5 cosine 15 gives us the initial velocity horizontally. Here's the 5, and that's the angle 15 right there. There's nothing more than remembering at this point. We already proved this earlier in the year, that when you want the x component of something, use cosine. And when you want the y component, use sine. We did that with vectors. We stated it again in the previous slide. So there's nothing more that I can do to help you here besides tell you, you need to remember that when you want the x component of something, multiply by the cosine of the angle. Okay, so we take the 5, which was the velocity to start, or the speed, and then we multiply by the cosine of 15 degrees. After that, what we can do is we can solve for time. Okay, in the x direction, remember, this is always the equation that we're going to use. It's never going to change, because the 1/2 at squared, where does it go? Why don't we have 1/2 at squared in the x direction? What's the reason behind that?
The acceleration is 0.
Yeah. There's no acceleration in the x direction, so this equation will always be used here. So what we're going to notice here is that we want to go ahead and solve for the value of time. This is 0. We assume that if he's going to go a distance of 4 meters horizontally, that his starting position is called 0, and this is called 4. What else could I have done with this problem? What could I call this instead? I can call this any number. I can call this 7. If this is a distance of 7, then this is a distance of 11. from some starting point. So again, for these types of problems, if we want to look at them, we could say to ourselves, what is our origin? And this was something I said last time. I talked to you about the fact, I think Mr. Donachek likes to do this, where he calls something an origin. So what are we going to call the origin? Maybe we'll call the starting point the origin. And this is the vertical, and that's the horizontal axis for this problem. So the starting point could be considered the origin right here. So the x0 is going to be 0. And where he ends up along this plane is going to be 4 meters to the right. That's why x is 4 meters here. And then v0x is given, so we can solve for t. So let's go ahead and solve that. We get x over v0x is equal to t. We're just going to divide it 2. So we take 4 and divide it by this entire quantity. Remember, on your calculator, this is an easy calculator mistake. 5 cos 15. If you're going to divide that into 4, you need to put parentheses around your 5 cos 15. This entire thing needs parentheses around it when you plug in down here, unless you evaluate this number first and then do 4 divided by a second answer and choose that answer. But remember that if you just do 4 divided by 5 times cos 15, the calculator will literally do that. It'll do 4, it'll divide it by 5 to get 0.8, and then it'll multiply that answer by cos 15, which is not what you want to do. So for this calculation on your calculator, remember please to put your denominator in parentheses if you're going to do it all in one step on the calculator. What else do I have to remember to have my calculator in? What mode? Degree mode. Okay, so go ahead and take a look, everybody. Hit mode on your calculator. Hit mode on your calculator and make sure degree is highlighted, not radian for now. If radian is highlighted, just change it. Go over to degree and hit enter on it. What do we get, Valentina? What did you get for a time?
4.8.
4.8?
Oh, wait, no, that's for 5.
Ah, gotcha.
So for time, I got 0.83.
All right. And notice, can you give me any more than that? 83 or?
0.828.
Okay, I'm going to keep a couple decimal spots because, again, time is not what I'm looking for in this problem. So it's not my final answer. That's what I mentioned about the quiz, the same thing. So as a result, I don't want to round this very far. I want to keep as many decimals. So in my calculator right now, I might just keep that answer in there with all those decimals and use that exact number later on in the calculations.
Is it okay if you just plug in the x over v0x?
Absolutely. So you can not even solve for this number, and you could take this expression for time, the one that I just circled there, and you could plug x over v0x into the other equation, which we're going to use now. So let's look at the y direction now. Remember, we are assuming that x equals 4 and trying to determine the y value, how far Tom Cruise falls. So let's take a look at our equation in the y direction. We've got this. Y equals y0 plus v0 yt plus 1/2 ayt squared. Remember, ay in this problem is always gravity. Okay, ay is always gravity, unless stated otherwise. Unless stated that you're on a different planet, or that you're in a field where there's air resistance, so gravity is a little bit less. Okay, but for now, negative 9.8. So in this problem now, I can go through this process and just literally go through the whole solution. I'm going to say y0 is 0 because I'm starting at what we're calling the origin. Now, our answer is going to be lower than where we started. So this number will definitely be what kind of a value? What kind of a value will it be, Christina? Negative. It'll be a negative quantity because it ends up below where it started. So that's 0. I'm going to cross that off. I'm then going to say, I'm looking for y. So this is a straight plug and chug. v0y. Now t is really x over v0x. That's what Maura was mentioning a moment ago. He replaced t with x over v0x. And you can do that. So again, let me point it with a color. He took this and plugged it in here and over here for time. And that's what we're seeing right here and right here plugged in for time. You can do that. Or you can take this number and plug it in for time as well. It's the same thing. One answer might seem slightly different due to rounding, and that's all you're going to notice in this problem. But it's the same process, whether you take the number, the expression here, or if you take even this whole expression right here. You can take that whole expression and plug it in. It's up to you to decide what you want to do.
Would v0y be 0?
VOY wouldn't be 0. This is the first time it won't be. For the quiz, it was, right? V0Y on the quiz was 0. How come it was 0 on the quiz? Why was V0Y 0 on the quiz? What do you think, Francisco? It was launched horizontally. That was the key to all horizontally fired problems. V0Y is always 0 because you're literally kicking it only with V0X. But this problem is Tom Cruise jumping at an angle. So the angle is what gives us a vertical component of velocity for this problem. So what is V0Y? Well, it's the same thing as V0X, except instead of cosine, what do I use? I use the other trig function, sine. So this becomes really V0 times sine of theta. That's what that value is. Then again, it's going to be times x over, well, this is V0 times cosine of theta. And this is 1/2 AY. And this is, again, really V0 cosine theta. And that whole thing is squared. So it looks really complicated because there's all these trig functions, right? But it's not bad. Plug in numbers at this point. You know this, 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 you know this. You know everything in this problem. Everything at this point is known. So go ahead and plug in for everything in that equation. So we got 5 times the sine of 15. X is going to be a 4 over 5. Notice I'm dropping units at this point in the year. You'll notice I do that because honestly these equations get crazy lengthy at this point. You should know your units. If they're standard, you're good. If they're all standard, you're good to start. So there's no need to show the units every single time here. Okay? So that's my equation right there, and that's my solution. It's going to give me a number. Okay? It's going to give me a number. I don't know if I did this in the vertical. Did I do it this way? I did. Okay. So we're going to get y equals negative 2.3 meters. Okay, you can check mine. I may have rounded earlier. I used 0.8282 for my time. But then I think it looks like I plugged in, then I plugged in the entire expression anyway, so it didn't matter in the end. So we get negative 2.3 meters. So what does that mean? What does that actually mean physically in this problem? Ben, what do you think?
I mean, it means that we don't know that his UTS there, his height is higher than -2.5.
Yeah. He's still how far above the 2.5? How far, man?
It's
0.2 meters. So go back to the problem. I know it's really small to see. I'm going to zoom in. So look, if he fell 2.5 meters, remember, he would end, I'm going to use green, he would end up right here. But he only fell 2.3 meters. So this is where Tom Cruise is at that moment. Let me undo that first one. So this is where he is right here. After traveling 4 meters horizontally, he's only fallen 2.3 meters. So he's going to make the jump in the end. Now, had we done it the other way, the other solution where we let y equal negative 2.5, the x value after y is 2.5, the x value would have been like 4.1 or 4.2, which means after he's fallen 2.5 meters, he's 4.1 or 4.2 meters away from where he started, which also would conclude that he does indeed make it. So either way we did this, he would make it. I'm not going to go through the second method right now for the sake of time, but I want to point that out, that your answer for the second methodology would have been something like x equals 4.2, 4.1, 4.3, somewhere where he just made the jump.
So if the change in y that you solve is actually greater than the variance,
Then he wouldn't, precisely. If this number were more than 2.5 in magnitude, like negative 2.7, if the number were negative 2.7, Tom Cruise would have ended up right here, somewhere below 2.5. If it were like 7, then he would have been all the way down here and clearly not made it, right?
So for both of them, it should be, no. For this one, it should be less than, and then for this one, it should be greater.
Yeah, so if you were solving this for y, we don't want our y displacement to be any more than 2.5. But if you let y equal negative 2.5 and you were solving for x, you want your x to be more than 4, because if it's less than 4, that means he's going to be ending up right here. Yep, good point. Okay, so depending upon the approach you take, you either want your answer to be less than or greater than the value that was given, but it depends on the approach. Yeah, Jack?
So since it's a point in space,
Exactly. Yeah, so if it was like negative 2.6, technically, he might still be able to grab on with his hands. And that's where you get into like more of AP physics where we look at size of objects. Here, we're just thinking about an object as a point in space. Very good question, Jack. Yep. I want to point something out. Let's take a quick look at this. And this is why I did substitution today. So let's take a look at this point of the equation right here. If you haven't written that equation down, jot it down real quick. Okay, jot this down right here real quick if you haven't written it down yet. You can jot that whole idea down. What I want to talk about is this. If I look at this equation, I'll notice a couple things. First, see how there's a V0 right here? Take a look where I'm pointing because it's going to go away. There's a V0 right here, and there's a V0 right here. What happens if you have V0 in the numerator and the denominator? They cancel. And what's sine over cosine? It's tangent. So really, this expression right here in the beginning becomes the following. Y equals x tangent theta. That's the entire expression in the beginning right there. Again, the V0s technically cancel, and then we're left with x, right? X times sine over cosine, or x times tangent. So this is really useful. We're going to keep going with this. The second part of it, I can simply distribute accordingly. So it's going to look like the following. We're going to get plus, and watch what I'm going to write this as. AY x squared over 2 V0 cos theta squared. All I'm doing is making it look prettier. That's it. The AY is going in the numerator with the x squared. And there it is. 1/2 is really like putting a 2 in the denominator. And there it is. And then V0 cosine theta is still squared. And that's it right there, squared. Write down in big letters below this. This is called the trajectory equation. Trajectory. This is something I think you should store in your calculator somewhere as a program. Something that you probably don't end up memorizing that's not on your formula sheet, but next year on the AP exam would be very useful. Okay, so learn how to write programs on your calculator so you can store extra equations. This is one of them that I would recommend that you do store on there. Again, this is called the trajectory equation. What variable does the trajectory equation not involve that is usually involved in almost all of these problems? Time. So write a note below this. Write a note below this. That this equation is very useful when you don't know time. When you don't know time, and you're trying to find one of the other variables in this equation. So say you're looking for x, or y, or theta, or v0. If you're looking for any of those values, or a, maybe you're on another planet, maybe you're trying to find the gravitational acceleration, a. But if you're looking for any of the other variables in this equation, theta would be tough to solve for because it's in 2 spots. We can do it on a calculator and let the calculator do the work for us, and we'll get to a problem with that eventually. But for this idea, I want you to recognize that time is not involved in the equation. It's a very useful equation to know going forward. Going forward. Okay, we're going to talk about another equation a little bit as well that is not on your formula sheet, but is one that I would recommend you know, whether it be memorizing it or honestly writing it as a program in your calculator for now. You can always derive this equation by doing what we did. You can take this expression right here, and you can plug it in like Maura had suggested earlier in those 2 spots, and then fill in this, and then simplify and cancel things, and you'll get it. But I don't want to take the work and the time to derive it every single time I'm using it on a test, so I would recommend memorizing it or having it stored in your calculator. It's not given on the formula sheet, you'll notice, if you looked at that earlier, so it's not something that the AP exam next year, or if you take the one later this year, is going to give you as an equation given. Okay? Yeah, Caroline.
Are you allowed to have formulas for that?
So on the AP exam, they do not clear memory anymore. It used to, when I was in high school, before an AP exam, the instructors would come by and actually clear your RAM on every calculator. It's not done. So can you have it? Sure. Now, if you put everything in existence in a program, you're never going to finish the test. And that's what they know. They know as an AP exam or an AP College Board program that the test is made in such a way that you need to fly through it. A physics AP exam next year, the APC one specifically, is made in such a fashion that you can't spend all day searching through programs and trying to read everything. So there have been students who will literally use a text editor and copy all the text from an entire chapter into a program. And they'll sit there and be looking for the answer. You spend 5-10 minutes searching through all the programs you have or all the stuff written, you're wasting that time. So if it were me, I would put in the key things. Like this is one of those key things I would have in there. We'll go over a couple more throughout the year and I'll say, hey, that's something you probably want to have in there so that you can quickly reference it when you need it. Okay? Same thing goes for there's a program stored already on your graphing calculator that can convert units. If you don't have it, you can get it from someone else in the class. You can transfer programs with a link cable. I have link cables next door. So there are programs already on your calculator, if you have not cleared the RAM and messed with it, that literally do unit conversions for you. So kilometers per hour to meters per second, let the calculator do the work for you on an AP exam. Don't do every single step, especially if it's a really complex conversion. If it's just centimeters per second to meters per second, do it by hand. That's really quick. But if it's meters per second squared to kilometers per hour squared, converting accelerations, that takes 3 to 4 steps along the way. I might just do it quickly on the calculator. Again, it depends on the student. If you're really good with your math, do it by hand. But if you think you might make a mistake somewhere along the way, then the conversion there would be useful. Good question. Any other questions on example 3? Let's go to example 4 so we can do it next. Similar type of problem. What I want to do is I want you to start again with the person next to you. We're looking at salmon. And salmon physically do this. They jump over waterfalls. I'm not making this up. Salmon swim upstream.
And bears standing there.
And they look huge. You ever seen, who was it that was talking about a salmon? Wasn't there somebody in here that was doing it or no? Was it a class? Somebody that's a fisherman and I think maybe it was alright. I was talking about a salmon that was this big. I've never seen a salmon that big. With the person next to you or around you in your area, start to talk about what is given and what you're looking for. Spend about a minute or two doing that, please. Start with the diagram.
I'm gonna jump off the waterfall. It's I did it right.
Check your diagram. You should be done with the diagram at this point, okay? You're done with the diagram at this point.
So to go by the lesson, we know is b minus. We go to delta y.
You talking about Mike Piazza right now, did you say? You talking about Mike Piazza?
Mike Piazza just agreed to manage the Italian national baseball team.
Did he really?
Yeah.
Piazza's a big Italian American, right? He's all about his heritage. The name alone tells you, right?
We need everything. That equation up there. We can figure it out. With this equation, Let's grab her.
acceleration is 9.8.
San Francisco, hold up.
X equals 2. Plug in X equals 6.
Plug in the accelerator. X times tangent equals 0.5. Opposite of opposite of please. 0.5/2 of theta. Okay. You got it. A. Acceleration in the y direction is minus.
Check your givens in line, please. Check your givens.
Like 6. Minus 9.8 times.
So we have 0.5, 2 times tangent 2.
So before you get to the solution, let's pause and talk about a couple things. Before you go on and figure out the equation you're going to use, let's pause and look. So, first, how many variables are missing for the overall problem? How many variables are missing for the overall problem? More. 2. Time and V0. Does the problem ask us how long it will take? Anywhere. So do we actually have to find time? So time does not matter in this problem, but we still have 2 unknowns. So we need to combine 2 equations. And if you think back to the previous problem, to get the trajectory equation, what did we do? We combined 2 equations. We combined our x equation with our y equation, and we came up with that trajectory equation. So we can do that all again. By all means, we can do it all again and spend all that time combining them. Or we can jump right to the trajectory equation at this point and try to find V0. Remember that V0 is the velocity with which the fish jumps, not the x or the y velocity, but the overall velocity. So V0 is missing right here, and it's missing right here in both of these terms. So I can start with this given, but I recognize that if I go through the x and the y directions, I'm going to get right back to the trajectory equation. So by all means, feel free to do x and y separately, find time, and I can easily find time. Well, not easily, but I can find time, and it'll be a function of V0, and then find time somewhere else, and then I have to combine the equations. So I would recommend the trajectory equation at this point. Now, before you jump into it and do it, let me ask the second follow-up question. If I only had the diagram, so imagine the problem's not given, okay? And only look at my diagram, please. Only look right here. Tell me another story or situation that could be represented by this diagram. Give me another sample example. Yeah.
If the salmon is a different story.
Different story, okay. Something else that could be described by that diagram.
I'm throwing an apple onto a shelf.
Perfect. You're throwing an apple onto a shelf. Never want to do that, but that works. I'm trying the bottle flip contest, right? You know the bottle flip? You're trying to get to land, and that really you want to elevate the body. You want to land on a higher ledge. Perfect. What else? What else, Jack? A high jumper. Love it. What else? What else? Come on. I can think of infinitely many. Christina, go ahead. A cannonball is launched at what?
And it has to like do a lot.
Sure, it has to hit castle wall. It's a big castle, right? What else?
When you go to the gym, you do like box jump.
You go to the gym, you do one of those box jumps where you land on the higher box. Where you jump to the ground and you have to land on the box. You kick a field goal and it goes to the field goal post. It goes above the field goal post. You shoot a basketball and it has to land exactly 0.5 feet. So do you follow what I'm getting at right now? What am I getting at? Let me summarize what I'm trying to say by having you look at this diagram over and over and over, annoyingly many times. What am I trying to get at here? What's the gist of this? What's the gist of it? Go ahead.
Well, the story doesn't really matter as long as you get the right values and you understand what it's saying.
So the story could be anything. It doesn't matter. So I want you guys to recognize that I can give you 5, 10, 20, 30, infinitely many more problems that all have the same diagram. Maybe this number is different. Maybe this number is different. Maybe the angle is different. I don't care. But I'm trying to point out the fact that the diagram can be used many times over. How else could the diagram look? Maybe you're starting at a higher elevation and ending lower. Then it would just be the reverse of this. It would look like this. And that's the cliff problem I talked about. But now, maybe it's fired at an angle from the cliff and it lands lower instead of fired horizontally. Right? You follow what I'm getting at here? Okay? So all these problems are about modeling. Modeling in the problem. Time is not involved. Don't use time in this problem. Jump right to the trajectory equation. Some of you started it already. We've got y equals x tan theta plus AYX squared over 2 parentheses V0 cos theta squared. And I think I've been starting to use theta 0 in my notes, so to be consistent. I've been using theta 0 as the initial angle. So to be consistent with my notes, I'm going to point that out right now. And there's a reason for that. I'm not just making it up. Okay, theta 0 I've been using to mean the initial angle of launch. Because when it lands, or at some other point in time, the angle of the trajectory changes, right? It goes up, then it starts coming back down. So the angle is always going to keep changing. So I've been using theta 0 a lot. So to be consistent with your work, theta 0 is used here. And then it just becomes, can we solve this, right? It's really just a messy solution. If I wanted to solve this algebraically, and I want to get v by itself, I got to do a little bit of math. So watch me for a minute, or do it with me. I'm going to do it algebraically, and then I'm going to talk about how it's a waste of your time to do it algebraically, and we'll show why. So I'm going to start doing it like this. I can subtract x tan theta from both sides. Okay, that's my starting point. I can do that first, move x tan theta over. But unfortunately, look, this is in the denominator, and I need v0, don't I? Is that what I'm looking for? So I'm going to invert both sides. I'm going to take the reciprocal of both sides. So I'm going to switch these two, and instead of having this over 1, I'm going to put this underneath 1 instead. So instead, I'm going to make this equation look like the following now. I'm going to say 1 over y minus x tan theta equals 2, and I'm going to distribute the v0, I'm going to distribute the squared to both terms. v0 squared cosine theta 0 squared all over AYX squared. Now remember, cosine theta squared is sometimes written as cosine squared theta. And you'll see that in pre-calculus and in the AP Calc courses. I'm putting it like this for now not to confuse anyone. That's the only reason I'm doing it. So if you're like, wait, in pre-calc we do cosine squared theta, that's fine. I just don't want people to be confused with the 2 here thinking it's something else. But this quantity is squared because both of these terms are squared. Now I'm going to go ahead and multiply both sides by AYX squared. Pretty much I'm going to get rid of this by moving it up to the numerator. You follow me? Algebraically, I'm going to move this to the numerator. And then what am I going to do with the 2 cosine theta 0 squared? How am I going to get rid of this when it's next to v0 squared? How am I going to get rid of it? What am I going to do? Mathematics. This is 9th grade math, guys. 9th grade math here. More. I'm going to divide by it. So I take this and I multiply by it. I'm going to take this and I'm going to divide by it. So the first term, or the left side term, becomes the following. AYX squared all over 2 cosine theta naught squared, parentheses, y minus x tan theta naught. And that's going to equal v0 squared. So how do I get v0 by itself if that equals v0 squared? I simply take the square root of both sides. Look at all the work it just took me to get v by itself. That's what I'm getting at. So if it's me and I'm taking this on a test, and I got to this point right here, I would let my calculator do all the work. Once I get this point here, I would plug in my values and let the calculator do the work. Okay, so it would look like the following if I let the calculator do the work. I would say 0.5 equals 2 tangent 32 plus negative 9.8 times 2 squared, I'm going to put 2 there even though I know it's 4, over 2 v0 cosine 32 squared. So that's what I'm going to do instead. And this is one of those few times that I'm not going to solve algebraically. Now sure, the algebraic solution is extremely powerful. I can see how velocity is affected by all of these parameters, right? If I look at this logically, this is why we did that density lab in the beginning of the year. If I look at this problem, I can see that the velocity initially is directly related to my acceleration. Directly related to it. The velocity itself is indirectly related to my angle because it's in the denominator. But you know what? This is subtraction, this is multiplication, so it can be kind of dually related in a sense. And then it's also indirectly related to the height needed. If I need more height, then I'm going to have to think about how it affects the velocity itself. So the direct and indirect relationships help. But for this problem, because there's so much going on with sine, with cosine, and with tangent, and with subtraction and square, it's not really useful to help you. So I would go about this process. Now, how do I solve this on the calculator? How do I solve this on the calculator? How do I solve the equation on the right in the calculator? That's what I would continue with, right? If I do another right. Nobody knows how to solve this on the calculator? Right. So let's talk about it. I talked about it freshman year, so you had me in class. Shame on you, freshman year. We did go over this one point in time. It's fine. Freshman year is a long time ago. Here's what I would do. In y1, I would put 0.5 because that's this right here, y1. And this is y2. So y2 is going to be written as the following. 2 tangent 32 plus negative 9.8. Now, instead of putting 2 squared, I'm just going to put 4. Okay, please, people, don't get confused. I've seen that a million times. Students are like, wait, what did you do there? You just squaring 2 to make that a 4. I just don't want to make it harder on the calculator input. Now, here's the thing. On the calculator, what key do you have to put in for an unknown variable? You can't put V0 in the calculator. It doesn't work. It doesn't exist. Francisco, you have to put X. So this is not X. Is that clear what I'm saying? On the calculator, though, you're going to call this X. And then you're going to put cosine 32, close the parentheses, and square it. So that's what's going to go in y1 and y2 right here. But write yourself a big note if you have to, that this is not displacement. This is your initial velocity. But on the calculator, all you can call it is X. And where is that X? On the calculator, that X is right below your mode button. Right below the button called mode on the calculator is where X lies. I'm going to quickly demonstrate it on mine so you can see it. Give me about, a minute to get it loaded up. What are you going to do once you have y1 and y2? Does anyone remember? Mora, nice. Intersect. You are going to find what we call the intersection of those two things. Remember, this is how you solve a system of equations. You look for where they intersect. Remember, you had 2 equations and 2 unknowns, and they were linear, and they intersected somewhere. And where they intersected was the solution. It's the same process we're taking here. This is simply substitution method from freshman year. But you could also solve that with looking at a graphing calculator. For the time being, please take a look at the board. I'm going to go ahead and switch over. Okay, for those that were a little confused, take a look at my calculator up here, please. Ignore what's already in here. I've been doing some other work. Okay. In y1, I put 0.5. In y2, I put this lengthy equation. So let me go through it with you if you're having trouble how to input this. I would start by doing this. Parentheses 2, tan, 32, close, close. That's the first term. And I'm going to go back to my overhead for you to see it, right? 2 tan 32 is right here. That's the first term that I'm putting in there into the first part. Then I've got a plus symbol. Now, this is where it's going to get really messy because I'm going to have parentheses within parentheses, right? So I need to add a very large term. Now, there's a key on the calculator to remember. For every open parentheses, you need a close parentheses. So if you forget where your parentheses are at, think about how that's going to work. And some calculators actually show you, like when you close the parentheses, which one you're closing. It'll like highlight it. Mine does not. So unfortunately, it doesn't show that. But I want you to see in general. So this is going to be open parentheses. I'm going to open it one more time for the numerator now. The numerator is negative 9.8 times 4. And then I'm done with the numerator, so I close my numerator. So notice I opened the entire thing that I'm going to add first. Then I wrote my numerator in parentheses, negative 9.8 times 4. That's the numerator. Then I'm going to put the division symbol, and now I'm going to put the denominator. The denominator is 2 times, and now I need another open parentheses, because this is going to be x cosine 32. Close the 32, close the x cosine 32, square it, close the whole denominator, close the entire fraction that you're adding on. So it looks really confusing, but if you step through it one step at a time, you'll see where everything is pointing out. So let me go through it here again. This right here is the numerator of the second part that we're adding in the trajectory equation. This is the entire denominator. I'm starting by putting open parentheses to make the denominator 2 times x cos 32, but I want to square x cos 32. So after I close the parentheses, and I'll backtrack to make it see it again. Okay, I'll backtrack. I close the angle 32. I close x cos 32, but I want to square x cos 32, so I square it. I then close the denominator, which is closing this parenthesis right here. But then I have to remember that I started this whole thing with an open parenthesis up here first. So then I close that as well. Now, my goal is to find the intersection. I don't know where it's going to intersect. So the way I start these problems is by hitting zoom, and I hit 6 for zoom standard, just to start. And if I don't see an intersection here, I'm going to then rescale. So it looks like I'm seeing some funkiness going on. Okay. I've got that side, and look, I've got the other side. So for those that know their functions, this is a rational function. If you remember from freshman year, rational functions look like this, or they look like this, or like this. That's what this is, the second graph. Because think about the original way we wrote it. It's all over x, and x is squared. So like 1 over x squared, that looked like this from freshman year. Okay, but we're going to take a look at this graph, and we see this is the rational function. Where is the constant function y1? What was y1 equal to? 0.5, right? So what would that look like? A line that says y equals 0.5, what does that look like? It's a horizontal line, and there it is. There's that horizontal line. So I can't see very well, so watch what I'm going to do. Some of you are not good on your calculator, so I really recommend you watch. I'm going to choose window to see a little better. And I know that my y max will not be greater than 0.5. So I'm going to make this 1 instead. And the y min, I'm going to make this equal to -3 for now. Then on the x scale, I'm going to leave it the way it was, so I can zoom in a little bit better. So now I can see this a little bit better. Now do you see the intersections more? What kind of a value am I going to look for? Well, take a look at the problem that was given. If I go back here, to get this answer, isn't it plus or minus outside of the square root, really? It's really plus or minus. Now, because I'm looking for the speed with which the salmon needs to jump, I'm looking at the positive answer. And we know that we're jumping at this angle. I'm not going to take a negative and then it's going to suddenly be jumping down into the water. It's jumping up toward the waterfall. So I know I'm looking for the positive answer. So I'm going to look for this intersection. Give me one more second. Second calc. To find the intersection, it's second and then trace. And then the number 5 for intersect. Now the key is you got to go over closer to the one intersection you want. Once you're near that intersection, just hit enter on the next one, then hit enter one more time, and it will find the intersection that you want. It may take a minute, and there it is. 6.02 is the velocity that the salmon has to jump with to get up. You see how it took us almost the whole period for one single problem? Okay, because I want to explain to you how things work, not just what the answers are. So V0 is 6.02 meters per second. We will continue next class with this idea. What should you do in this time now? Start doing the homework problems that are launched at an angle, the ones with the asterisks next to them. Start on those problems now at this point. We'll continue. We have 2 more classes still with this topic. 2 more full classes, and then comes your test. So keep in mind where you're at time-wise. Office hours after school today in this room. So it's always Tuesday and Wednesday. So I'm going to 6 weeks. Tomorrow,